A triangle is a shape with 3 sides and 3 angles. An equilateral triangle is a special type of triangle that's got 3 equal sides and 3 equal angles. On the diagram, to show that the sides are equal, we mark them like this. Because the angles are all equal, they will all be 60 degrees. An isosceles triangle has 2 equal sides and 2 equal angles. Here we've got 2 different isosceles triangles. Again, we can show that these 2 sides are equal by marking them like this, or you might sometimes see them marked like this. We have 2 equal angles on this triangle, here and here, and on this one the 2 equal angles are here and here. A scalene triangle has no equal sides and no equal angles. Here are 2 examples of scalene triangles, and there's no special markings we can put on these. The final type of triangle. A triangle is a shape with 3 sides and 3 angles. An equilateral triangle is a special type of triangle that's got 3 equal sides and 3 equal angles. On the diagram, to show that the sides are equal, we mark them like this. Because the angles are all equal, they will all be 60 degrees. An isosceles triangle has 2 equal sides and 2 equal angles. Here we've got 2 different isosceles triangles. Again, we can show that these 2 sides are equal by marking them like this, or you might sometimes see them marked like this. We have 2 equal angles on this triangle, here and here, and on this one the 2 equal angles are here and here. A scalene triangle has no equal sides and no equal angles. Here are 2 examples of scalene triangles, and there's no special markings we can put on these. The final type of triangle is a right-angled triangle, and this has got 1 right angle, which is 90 degrees. We show these with little squares. Just out of interest, you might have noticed that these right-angled triangles here are also scalene as well, because they've got no equal sides and no equal angles. We call them right-angled triangles though, because they've got the special property of having a right angle. Take a moment to make sure that you can identify all of the special types of triangle. Here's a question for you. You'll need to copy out the table and then put the letters corresponding to the triangles in the correct sections. Press pause and have a go. When you're ready, press play. Here are the answers. We say that lines are parallel if they will never meet. Here are some examples of parallel lines. You might like to think about them as being the sides of a ladder or train tracks. We mark parallel lines with little arrows, like this, or like this. The word parallel even gives you a clue as to what parallel lines are. If you look at it carefully, you'll see that you've got a pair of parallel lines formed by the 2 L's here. Lines are called perpendicular if they meet at a right angle. Remember, a right angle is 90 degrees. So these are perpendicular, and so are these. We mark a right angle with a little square, like this. A quadrilateral is a shape with 4 sides and 4 angles. There are 7 special quadrilaterals. Here they all are. I'm now going to go through some of the properties that these quadrilaterals have. Here are the properties of those 7 special types of quadrilateral. You need to take a moment now to memorize all of them so that you're able to identify the quadrilaterals. Press pause and do this. When you're ready, press play. Now for this question, you're going to need a sketch of each of the 7 shapes. What I want you to do is put on the special markings for the shapes. I'm going to put the markings on the parallelogram for you. I've got 2 pairs of equal sides, so this side is equal to this side, and this side here is equal to this side. Notice that because this pair is different to this pair, I've used double markings for this one. We've got 2 pairs of equal angles as well, so this angle's the same as this one, and this one is the same as this one. Again, notice that because these angles are different to these ones, I've used double markings for the separate pair. I've also got 2 pairs of parallel sides, so this side is parallel to this side, and this one is parallel to this one. And in the same way, I've used double arrows for the separate pair. Now put the markings on the rest of the shapes yourself. Press pause and have a go. When you're ready, press play. Here are the answers. Here's another question for you. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Let's say your pet parrot went missing. How would the local newspaper report this? They'd probably print the headline, Polygon. Of course, this isn't actually what it means. In maths, it actually means a shape with many angles. Here are some examples of polygons. As you can see, they're all shapes with many angles. Now, these particular ones are regular polygons. Regular means that all the sides are equal in length for that particular polygon, and all the angles are equal in size for that polygon. So, for example, on this triangle here, all the sides are equal, and all of the angles will be 60 degrees. On this square here, all the sides are equal, and this time, all the angles will be 90 degrees. It's useful to know the names of these polygons. So, a regular 3-sided triangle is an equilateral triangle. You should already know a square. A 5-sided polygon is called a pentagon. If it has 6 sides, it's a hexagon. 7 sides has 2 names. It's either a heptagon or a septagon, and you'll see both of these used. And 8 sides means that it's an octagon. Just out of interest, a shape with 9 sides is called a nonagon, with 10 sides is called a decagon, with 11 sides is called an undecagon, and with 12 sides is called a dodecagon. Now here are some questions about polygons for you. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. You can also get irregular polygons. These are where the sides can be different lengths and the angles can be different sizes. This one here has 5 sides, so it's still a pentagon, and this one has 6 sides, so it's still a hexagon. More formally, we call them an irregular pentagon and an irregular hexagon. Here's a question for you now. Match up each of the shapes to the 6 names around the outside. Press pause and have a go. When you're ready, press play. Here are the answers. In this clip, we're going to be looking at the 3 types of symmetry. Line symmetry, this is on 2D shapes. Planes of symmetry, this is on 3D shapes. And rotational symmetry, and again this is for 2D shapes. Let's start with line symmetry. Looking at this square, a line of symmetry is anywhere that you could fold the square so that it folds exactly onto itself. So here's one line. There's another one here. One corner to corner in this direction. And another one in this direction. So on a square, there are 4 lines of symmetry. Now write down how many lines of symmetry there are on this rectangle. Press pause and have a go. When you're ready, press play. You should have found 2. A lot of people think that this is a line of symmetry on a rectangle, but if you try folding it over, you'll see that it doesn't match up. So the rectangle only has 2 lines of symmetry. It doesn't have any diagonal lines. Here's another one for you to try. Press pause and have a go. When you're ready, press play. There are 6 lines of symmetry on a regular hexagon. Now we're going to look at planes of symmetry. This is the same sort of idea as line symmetry, but in 3 dimensions. So a plane of symmetry on this cuboid would look like this. To draw the plane of symmetry, we need to imagine slicing this shape into 2 identical pieces. You can't just draw one line down the front. You've got to draw all the cuts. Another plane of symmetry would look like this. Or this. Any of these 3 planes of symmetry would have been a correct answer. Here's a question for you to try now. To help you copy out the triangular prism, here it is on squared paper. You need to copy this and then draw one plane of symmetry. Press pause and have a go. When you're ready, press play. Here's one possible answer. And here's another one. Finally, we're going to look at rotational symmetry. The order of rotational symmetry of a shape is the number of times it fits onto itself in a full 360-degree rotation. To find the order of rotational symmetry of a shape, tracing paper is helpful. So I put my tracing paper over my shape and trace it. I then draw a little arrow so that I know where I started. Now I'm going to rotate my tracing paper and see how many times the shape fits back onto itself. Once, twice, 3 times, 4 times. So the first shape has rotational symmetry order 4. Let's look at the second shape in the same way. So I trace it and draw a little arrow. Then I can start rotating the paper. That's once, twice. So the rectangle has rotational symmetry order 2. Let's do the last one in the same way. So we trace it, put on the little arrow, remember, and then we start rotating. Now this one only fits back onto itself when it gets back to where it started. Because these 2 shapes fit back onto themselves more than once, we say that they've got rotational symmetry and we can work out the order. Because this one only fit back onto itself when it got back to the beginning again, we say that this has no rotational symmetry. Here's a question for you to try. You need to find the order of rotational symmetry of each of these shapes. Because you're doing this on a screen in front of you, you need to know that all of these angles are equal, all of these angles here are equal, and this is a perfect square. Be careful with the middle one. Press pause and have a go. When you're ready, press play. Here are the answers. I hope you spotted the trick on the middle one. This flag here is the wrong way round, so this has no rotational symmetry. Finally, here's an exam-style question for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. We say that a shape will tessellate if it can be fitted together to form a repeating pattern with no gaps at all that can be continued forever. We call the final pattern a tessellation. One way of thinking about it is thinking about tiling a floor. Here are some examples of tessellations. In each one you should spot that there's a repeating pattern, there's no gaps, and that they could be continued forever across the page. This is an exam-style question on tessellation. I want to show how this shape will tessellate. Notice that it tells me to use 6 more shapes. That means my final picture must have this shape and 6 more, making at least 7 altogether. Before I show you a correct tessellation, I want to show you some very common wrong answers for this particular shape. You might start by lining them up like this, and then continue, making what looks like a flower pattern. The problem is when you get here, although it looks like it's going to fit, the gap is actually too small, and we're going to end up with an incorrect tessellation. Let me show you another mistake. You could put a shape here and spot that you'll nicely fit another 2 here. So far it's looking pretty good. Shapes will fit round the edges like this, and we're getting more confident and thinking, yep, I've got it this time. But it won't actually fit. If we move this in, we can see that our shapes are overlapping. So again, this is another incorrect tessellation. What you need to do is turn the shape upside down like this and then fit them together like this. You can then repeat this over and over, making your tessellation with 7 shapes in total. If you wanted to, you could repeat this pattern all the way across the page. And shading it in really highlights the pattern you've made. Obviously, on the exam, you don't have to colour it in. This just helps you see on the screen the pattern of the shapes. Here's one for you to try. You'll need to copy the shape carefully onto some squared paper and then try to tessellate it. Press pause and have a go. When you're ready, press play. You're asked to do at least 5 more shapes, giving 6 in total. This is one possible answer. You can continue this pattern all the way across the page. Like this. Your answer should look like a section of this complete pattern. Here's another one for you to try. Again, you need to copy the shape very carefully onto some squared paper and then try to complete the tessellation. Press pause and have a go. When you're ready, press play. Here's an answer using 5 more shapes. And if you want, you can continue it to fill in the space. In maths, we have a special word, congruent. It sounds like a really difficult word, but the meaning of it is straightforward. 2 shapes are congruent if they're identical in size and shape. So, for example, these 3 shapes here are all congruent because we can see that if we rotated or flipped this one, it would fit on both here and here. So they're all the same size and the same shape. This one is not congruent to these because although it is the same shape, it's not the same size. This one is not congruent to these because although it is the same size, it's not the same shape. Here are 2 questions for you to try now. Press pause and have a go. When you're ready, press play. Here are the answers. An angle is a measurement of turn. 1 complete turn is 360 degrees. There are 4 names of different types of angles that you need to learn: acute angle, right angle, obtuse angle, and reflex angle. First of all, you need to understand what a right angle is. A right angle is exactly 90 degrees, so it makes a square corner and it's shown like this. Now, right angles can be any way around, so this is a right angle as well, and so is this. We don't have any left angles because it's a different type of right. It actually means it's the correct angle, because builders have to build walls at right angles, so these walls are built right. An acute angle is any angle that's less than 90 degrees. Acute actually means sharp, so this is a sharp angle. In normal life, we talk about an acute pain, which means a sharp pain, or an acute sense of humour, which means that someone's got a sharp sense of humour. You might also like to remember that the angle is small, and so therefore it's cute. An obtuse angle is more than 90 degrees, but less than 180 degrees. Now, in normal language, we say that someone's obtuse if they're being a bit thick. So remember that an obtuse angle is a thick angle. Finally, a reflex angle is more than 180 degrees, but less than 360 degrees. A doctor might check your reflexes. Think about the angle made at the knee by the upper leg and the lower leg. Here's a summary of the 4 names of angles that you need to learn. Here are some questions for you to try now. Press pause and have a go. When you're ready, press play. Here are the answers. In this clip, we're going to be looking at the properties of solid shapes. First of all, we need to have a look at all the shapes that we're concerned with. The first one is a cube. We can think of a cube as a square in 3D, where all of the lengths are exactly the same. The next shape we need to know is a cuboid. A cuboid can be thought of as a rectangle in 3D. The next solid shape we need to look at is a triangular prism. You can think of this as a triangle in 3D. And you also need to know a cylinder. And I'm sure that you can see that this is a circle stretched out to form a 3D shape. Now, these are all special types of 3D shapes. They're called prisms, and a prism has the same cross-section all the way through. What this actually means is that if you put it into a bacon slicer, you would always get the same shape. So if you imagine taking slices off the cuboid, you'll see that you always get a rectangle. So for the cube, the cross-section is a square. For the cuboid, it's a rectangle. For the triangular prism, it's a triangle. And for the cylinder, the cross-section is a circle. Here are some examples of 3D shapes that are not prisms. We have a square-based pyramid, where we've got a square on the base, forming a pyramid above it. A triangle-based pyramid is similar, but it has a triangle at the base. Out of interest, if the triangles that form the triangle-based pyramid are all equilateral, then it's actually called a tetrahedron. We also have a cone. You can think of a cone as being a pyramid with a circular base. And then finally, we have a sphere, which is the shape of a ball. So to summarise, here are all the 3D shapes that you will need to know the names of for your exam. Now, I want to fill in this little table. I'm being asked about a cube, and I want to know how many faces, edges, and vertices it has. Before we worry about what this actually means, let's draw a little sketch of a cube. So remember, it's a 3D square. So if I start with a square and then take some lines back from each corner, I can turn it into a cube. Faces means the flat sides, like this front part here. So I need to work out how many faces there are by counting the flat sides on my sketch. I can see that I've got one at the front and one at the back, one at the top and one at the bottom, and one on the left and one on the right. So that's 6 altogether. If you think about a dice, which is always in the shape of a cube, it becomes obvious that there are 6 faces because the numbers on a dice always go up to 6. The edges are where 2 flat sides meet. So for example, this is an edge. This is another edge. So to calculate how many edges there are, I need to count them on the diagram. So I've already got 2. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 edges. Another way to get this answer is to think that the cube is a square joined to another square by 4 edges. So we have 4 edges on our original square, 4 edges on our back square, and 4 edges joining them together. And that gives us a total of 12 edges. Now the most difficult word up here is vertices, but this just means corners. One way of remembering this is that the V at the front actually makes a corner to remind you. This is the plural. If you've just got one corner, it's called a vertex. Now I want to count all the vertices on my cube. Remember, that's just the corners. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 vertices on my cube. Now you need to fill in the table for these 3D shapes. It will help you to sketch one each time. Press pause and have a go. When you're ready, press play. Here are the answers. I'm being asked to draw a net of this cuboid on the centimetre grid. A net means what this would look like if it was unfolded. It helps to draw in the lines that you can't see. This helps me to identify how many faces I've got. I've got a base and a top that are the same as each other, a front and a back, and they're the same as each other, and a left-hand side and a right-hand side, and they're the same as each other as well. When I draw my net, I like to start with the base. We can see that the base is a 2 by 3 rectangle. I draw this somewhere in the middle of my squared paper. Now I'm going to draw on the right-hand side. This is a 3 by 4 rectangle, so I line it up with one of the sides of the base that's 3 centimetres long. The left-hand side is the same size as the right-hand side, and it just goes on the other side of the base. For the back, we have a 2 by 4 rectangle, and this lines up with one of the sides of the base that is 2 centimetres long. For the front, we have the same thing on the other side of the base. There's only one thing left to put on now, and that's the top. This could go here, 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 or here. On my picture, I've only got space here, so I draw it in and notice that it's the same size as the base. This is the finished net. If I was to cut this out of cardboard, I would be able to fold it up to make this cuboid. Here's one for you to try. Press pause and have a go. When you're ready, press play. Here's one possible answer. Obviously, you could have put your top here, 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 or here like I have. Finally, here's one more for you to try drawing. Press pause and have a go. When you're ready, press play. Here's one possible net. I hope you realised that when you drew in the lines that you can't see, you get 5 faces. 3 of them are rectangles, and we've got 2 triangles. The base is 3 by 4, that's here. The left-hand side is 4 by 4, that's here. And the slopey bit is 4 by 5, that's here. The front and back triangles are identical, and they're here and here. You should already know that the angle on a straight line is 180 degrees. So, if we have more than one angle on a straight line, we know that they must add up to 180 degrees. We can use this fact to calculate missing angles. So here we have a straight line, and we have one angle of 40 degrees. We know that it has to add up to 180. So to calculate this angle here, we can do 180 minus 40. That gives us 140. So this angle here is 140 degrees. If you want to check, you can add them up and see that they definitely add up to 180 degrees. In this question, we still have a straight line, but this time we've got 3 angles and we want to work out this one here. I start by adding these 2 together. So I've got 55 plus 50. That's 105. Now I know it's got to be 180 because it's a straight line. So I do 180, take away 105, and I get 75. So the missing angle here is 75 degrees. Here's an exam-style question for you to try. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. Here's another one for you to try. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. Here's a slightly more difficult question for you, but you're still going to be using the same fact. Press pause and have a go at it. When you're ready, press play. Here's my answer for this question. Obviously, you don't have to write exactly the same sentence as I've written, but you need to say that the angles add up to 170 degrees and that this isn't 180 degrees, so it's not a straight line. You should also know that the angles at a point add up to 360 degrees because they make a full turn. We can use this fact to calculate this missing angle. So I start by adding these 3 together. I've got 90 plus 60 plus 100, and that's 250. I can then take this away from 360. And I get 110. So the missing angle here is 110 degrees. Here's an exam-style question for you to try. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. Here's another one for you to try. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. For this one, you needed to remember that this tells you that the angle here is a right angle, which is 90 degrees. An angle is actually a measure of rotation. Any angle that's less than 90 degrees is called an acute angle. When we get to exactly 90 degrees, that's a right angle. Angles that are bigger than 90 degrees but less than 180 degrees are obtuse angles. The angle on a straight line is 180 degrees. An angle bigger than 180 degrees but less than 360 degrees is a reflex angle. And once we've been through a full turn, that's 360 degrees. Now you know what an angle really is, you should be able to answer this question easily. Press pause and have a go. When you're ready, press play. Angle A is the bigger angle, because to go from here to here, I've rotated further than from here to here. I'm now going to show you how to measure angles. To do this, we need a protractor. The protractor needs to be positioned like this, so that the centre mark is on the point of the angle and the baseline is running along the bottom line of the angle. Notice that there are two scales on the protractor, the inside track and the outside track. You need to decide which scale to use. The baseline is lined up with the 0 on the outside track, so we're going to use the outside track for this angle. We can see that this angle is 70 degrees. It also helps that we're told that it's an acute angle. We know it's got to be less than 90, so 70 sounds about right. Now I want to measure this obtuse angle. Remember that obtuse means more than 90 but less than 180, so I'm expecting an answer in that region. I put my protractor on, lining this part up carefully and the baseline carefully. I can see that the line is with the 0 on the outside track, so I'm using the outside track. And my answer is here. To help me read this, I'm just going to enlarge it. I can see that it's at 125. So the answer is 125 degrees. Remember, I was expecting something in between 90 and 180, so this fits with what I was expecting. You might be wondering why we've got two scales on the protractor. That's because you can actually position your protractor like this as well and measure using the inside scale instead of the outside scale. You still get 125 degrees. Here's a question for you to try now. You need to copy the angle very carefully onto some squared paper and then measure the size of it. Press pause and have a go. When you're ready, press play. Here's the answer. I've measured the angle to be 106 degrees, but there is a bit of leeway here. You can have 105, 106 or 107. Now I want to measure the reflex angle ABC. That's actually this angle here. My problem is that this angle is bigger than 180 degrees, and of course my protractor only goes up to 180. There are two ways to solve the problem. The first way is to measure this angle here, which I can see is 125 degrees. So I know that this part here is 125. A full turn is 360 degrees, so to get this part, I can do 360, take away 125. That gives me 235 degrees. So the size of the reflex angle is 235 degrees. The other way of finding the size of the reflex angle is to extend one of the lines. I'm going to do this one. Now I know that we've got a straight line, so this part must be 180 degrees. What I can do now is measure this and add it on to 180. This time I'm going to be using the inside track on the protractor because the line is lined up with the 0 on the inside. I can see that this is 55 degrees. So I've got 55 degrees here and 180 degrees here. 180 plus 55 is 235 degrees. So again, the size of the reflex angle is 235 degrees. Here's one for you to try. You need to copy it out onto squared paper carefully and then measure this angle here. Press pause and have a go. When you're ready, press play. Here's the answer. Again, there's a bit of leeway here, so you can have 296, 297 or 298. Remember, there were two ways to do it. You could have measured this angle here and then taken away from 360, or you could have measured this angle here and then added this on to 180. Now let's look at drawing angles. The first thing I need to do is draw a baseline. This can be any length you want. Once you've drawn this line, you need your protractor. This part of the protractor needs to be lined up with either end of your baseline. If you put it on this side, you're going to use the outside scale. If you choose to put it the other side, then you'll be using the inside scale. You now need to find 75 degrees and put a dot. Then you can take the protractor out of the way and join the dot to the end of the line. So this is our angle of 75 degrees. Here's one for you to try. We're given letters here. Because B is in the middle, that's telling you that you need to draw the angle here. Press pause and have a go. When you're ready, press play. Your answer should look something like this. I now want to draw an angle of 255 degrees. This is a reflex angle, so it's a little bit more difficult to draw. I start in the same way though, with the baseline. So this is the baseline, and I want to draw the angle here. I'm going to extend the baseline now. And now I know that I've got 180 degrees here. All I need to do is draw a bit more to make 255. To work out how much more I need to draw, I'm going to do 255, take away 180. That's 75 degrees, so I need to draw 75 degrees here. So I put my protractor on. The 0 lines up with the line that I've just extended. I need to find 75 degrees, and I'm going to use the outside track. So that's here. Now I can take the protractor out of the way and draw my line here. So this is my angle of 255 degrees. There is another way I could have done it, of course, and that's to do 360 take away 255. That gives me 105 degrees. If I draw an angle of 105 degrees, which is here, then we know that this part must be the reflex angle of 255 degrees. Here's one for you to try. Press pause and have a go. When you're ready, press play. Your answer could look like this, or this. In this clip, we're going to be looking at drawing triangles using a protractor. In the question here, I'm asked to draw a triangle ABC, and I'm told that AB has a length of 8 centimetres, the angle CAB is 45 degrees, and the angle ABC is 58 degrees. Before I draw it properly, I'm going to do a little sketch. So I know it's going to be a triangle, and I know it's a triangle with corners A, B, and C. Length AB is 8 centimetres, so this bit here needs to be 8 centimetres long. Angle CAB, which is this one here, CAB, is going to be 45 degrees. And angle ABC, that's ABC, so that's that one there, is 58 degrees. Now that I've got my little sketch, I'm ready to start drawing this triangle properly. So I'm going to start by drawing the baseline here, and I'll need a ruler to do this. The baseline is 8 centimetres long, so I draw a line 8 centimetres long using my ruler. Now I need to draw an angle of 45 degrees on this side of the line and an angle of 58 degrees on this side of the line. I'm going to start with the 45-degree angle. So I need a protractor to do this. I'm going to move it into position on the end of my line, like this. I can then count round from the 0 to 45 degrees and put a blob. Now I can take the protractor out of the way and join the end of the line to the dot. I'm going to go through the dot a little bit because I don't know how long this side is actually going to be. Now I'm ready to do the angle on the other side. So I set the protractor up, and this time I want to measure an angle of 58 degrees. So I count from the 0 here this time to 58 and put a blob. Again, I'm going to move the protractor out of the way. Now I can join this end of the line to the blob, and I can carry on a little bit because it needs to meet this line that I drew before. Like this. Now you can see that I've got my triangle. I need to label it now with A, B, C, 8 centimetres, 45 degrees and 58 degrees. So it looks like this. Finally, I just checked my answer against my original sketch, and you can see that I've got all the details that I was expecting. So this is my final triangle. Here's one for you to try now. Press pause and have a go. When you're ready, press play. This is what your finished triangle should look like. If you want to double check it, one way to do that is to measure this angle here. It should be 43 degrees. Don't worry if you don't get exactly 43 degrees. Anything from 42 to 44 degrees tells you that you've drawn your triangle accurately enough. Before we look at reflections, you need to be able to identify the equations of straight lines. Line A has the equation x equals 3 because it goes through the x-axis at the 3. Line B has equation y equals 1 because it goes through the y-axis at the 1. You also need to learn the equations of these two lines. A is the line y equals x, and B is the line y equals minus x. For my first reflection, I want to reflect this triangle in the y-axis. So I need to imagine I've got a mirror here. Now, to reflect this shape in this line, I'm going to count from each corner to the line. So for this corner here, it's 1, 2, 3, 4, 5. So I need to go 5 away from the line, which is here. I do the same thing for each corner. So this is 3 away from the line, so I go 3 in this direction. And this corner is 5 away from the line, so I go 5 in this direction. I can then join these up to make my finished reflection. Here's the answer. Here's one for you to try. You'll need to copy the picture onto some squared paper before you do the reflection. Press pause and have a go. When you're ready, press play. Here's the answer. This time, I want to reflect the triangle in the line y equals x. So the first thing I need to do is draw this line. There are a few ways of getting the reflection now. My preferred method is to count from each corner across to the line, then turn the corner and go down. So, this corner is 1, 2, 3, 4 to the line. So now I go 4 down, 1, 2, 3, 4, and this is the new corner. In the same way, for this one, it's 6 across to the line, so I need to go 6 down, and here's the new corner. And for this one, it's 10 across to the line, so I need to go 10 down. I can now join these 3 points together. This is the finished reflection. Here's one for you to try. You'll need to copy the picture onto some squared paper first. Press pause and have a go. When you're ready, press play. Here's the answer. Finally, here's an exam-style question for you to try. You'll need to copy the picture out onto some squared paper first. You might find a piece of tracing paper helpful for this one. Press pause and have a go. When you're ready, press play. The first step is to reflect triangle A in the x-axis. This gives you triangle B, which is here. Then we need the line x equals 1 for the next reflection. That's here. And we reflect B in this line to give triangle C. To finish the question now, we need to describe the single transformation that maps triangle A to triangle C. You should be able to spot that to get from A to C, it's actually a rotation, 180 degrees, so we don't need a direction, and we just need to find the centre to finish off. You can use tracing paper to help you with this. The centre is here at the point 1, 0. So this is the final answer for the question. In this question, I'm being asked to rotate the triangle 90 degrees clockwise with centre 1, 0. So the first thing I do is mark my centre. Now, to be able to perform the rotation, I need a piece of tracing paper. I need to put it so that it covers the centre and the shape. Now I trace the shape onto the tracing paper. Now I put my pencil here to act as a pivot point, and then perform the rotation. It needs to turn in a clockwise direction, that's this way, 90 degrees, which is a quarter turn. I now need to draw this triangle onto my picture. Taking the tracing paper out of the way, I get this. This is my finished rotation. Here's one for you to try. You'll need to copy the picture onto some squared paper. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. Again, you'll need to copy it onto squared paper first. Press pause and have a go. When you're ready, press play. Here's the answer. Notice that in this one, the question didn't say clockwise or anti-clockwise, because when you're doing a 180-degree rotation, it doesn't matter which way you go. In this question, I'm asked to describe fully the single transformation that maps triangle A onto triangle B. This is often worth 3 marks in the exam. You need to say what type of transformation it is first. We can see that this one is a rotation, so we start with that. And that would be worth 1 of the 3 marks. We then need to say how much it's rotated and in which direction. From A to B, I can see is clockwise, and it's 90 degrees. This would get you the 2nd mark. For the last mark, you need to find the centre of rotation. This is often the awkward bit, and you need to use tracing paper to help you with this. So I get my piece of tracing paper, put it onto the picture, and trace triangle A. Now I need to take a guess at where I think the centre of rotation is likely to be. I'm going to try this point here. Now I move the tracing paper, and you can see that it's not going to line up with triangle B. So I need to go back to the start and try a different point. So I'm going to try this one now. Again, this one misses. So I go back again and try a different point. This one works, so this must be the centre of rotation. The point is 2, 1. I need to just put this up here, centre 2, 1. This is the last mark for the 3-mark question. Finally, here's one of those for you to try. You'll need to copy the picture onto some squared paper. Press pause and have a go. When you're ready, press play. Here's the answer. In the first question here, I'm being asked to translate the shape A by this vector and label it B. Translate means you just have to slide the shape around. This is actually a set of instructions for how you need to slide it. The number at the top is telling you to move it 6 across to the right, and the number at the bottom is telling you to move it 2 down. To do this, I use tracing paper to help me. I need to put the tracing paper over the shape and trace it. I can then slide my tracing paper 6 right and 2 down. This is the new position of my shape. I just need to label it B to finish off. For the second part, I want to translate shape A again by this vector. This is telling me to move it 4 to the left, and this is telling me to move it 1 up. So with my tracing paper again, I move the shape 4 left and 1 up. This is the new position. And to finish, I can label it C. The only difficult bit about translation is remembering which way the vector is telling you to move. I remember it like this. The top number relates to the x-axis. You can see that we've got the positive numbers in this direction and the negative numbers in this direction. The bottom number relates to the y-axis. Again, with positive numbers going up and negative numbers going down. So if I had a vector like this, that's a positive 2, so it's 2 to the right, and a negative 4, so it's 4 down. Another example would be that this vector has a negative 5 here, so that's 5 to the left, and a positive 6 here, so that's 6 up. Here are some for you to try. You'll need to draw the picture carefully onto some squared paper first. Press pause and have a go. When you're ready, press play. Here are the answers. Sometimes you might get a question like this, where you're asked to describe the transformation. I want to take triangle A to triangle C. I can see that this is a translation. The only other piece of information I need is the vector that it's been translated by. To find this, I can use my tracing paper. So I trace the shape A and see how I need to move it to get to C. Across first by 1 to the left, and then up 5. So the vector was 1 to the left, that's -1, and up 5. This is my finished description. Here's your final question. Press pause and have a go. When you're ready, press play. Here are the answers. This is a model made out of 5 little cubes. I can draw 3 different views of this model. If I was standing here and looking at this model, I would be able to see these 3 cubes. I've shaded them in to help me see. The front elevation is a 2D representation of what I can see from this direction. So I can see these 2 cubes here, and then this one sticking out on the side. So my drawing looks like this. Here are the two cubes, and here's the one sticking out on the side. So that's my front elevation. If I'm looking from this direction, then I can see these two and these two. Again, I need to draw what I can see as a 2D picture. So this matches up with this, and these two are here. So this is the side elevation. Finally, the view looking down on the object from the top is called the plan. By convention, the plan is what you would see if you were standing at the front and looking down on top of the object. So we'd see this square here and these three as well. So this square is here right at the front of the picture, and then these three are here. Another way to think of the plan is that it's a bird's eye view of the object. So to summarise, this is what I see from the front, this is from the side, and the plan is my bird's eye view of the object. Now this is an exam style question. In the exam, they'll give you an arrow telling you where the front of the object is. So in this question, you're just asked for the front elevation. You don't have to draw all three views. Press pause and have a go. When you're ready, press play. Here's the answer. We have these three here, and then this one sticking out here. This time you have the same object, but you're asked to draw the plan. Remember, this is the bird's eye view. Press pause and have a go. When you're ready, press play. To draw the plan, remember, imagine that you're standing at the front, looking down onto the object. We've got this one here, this one behind it here, and then this one sticking out here. Here's another question for you, but this time without the cubes. Press pause and have a go. When you're ready, press play. Looking from this direction, we can definitely see this bit here, which is a 3x1 rectangle. So that would look like that. Now, a lot of people think that this is the answer, but because this is taller at the back, you can actually see the height here. This is 2 centimetres compared to this 1 centimetre, so you need to do an extra centimetre here. This part is actually the sloping part here. I'm just going to neaten this picture up. This should be what your finished front elevation looks like. This time, draw the plan. Press pause and have a go. When you're ready, press play. Here's the answer. Remember, this is the bird's eye view. Now in this question, I want to do the opposite of what we've just done. I'm given the three views, and I want to draw a sketch of the 3D object. My advice for this is to start with the front elevation. Remember, it's just a sketch, so you don't have to be really neat. Now, using the side elevation, I can see that it goes back 2 cubes. It's 2 cubes wide in this direction. So I'm going to do that just by extending my front elevation. So this is the finished sketch. To check it, I'm just going to see that the plan matches. I've got these 2 here and these 4 here. And here's one of the other alternative possible answers. Finally, here's one of those for you to try. Press pause and have a go. When you're ready, press play. Here are 2 possible answers. In this clip, we're going to be looking at perimeters. The perimeter of a shape is the distance all the way around the outside of it. So for this specific example, you might like to think about a little man walking all the way around the shape. So first of all, he would walk along here, So far he's walked 8 centimetres. Then he walks along here, and that's another 3 centimetres. Then he needs to walk along here. Now, because this is a rectangle, this distance will be the same as this, so this is going to be 8 centimetres. So that's another 8 centimetres added to the total. And finally, he needs to walk along here to get back to the beginning. Again, because this is a rectangle, this will be 3 centimetres. And that's another 3 centimetres to add to our running total. If we add these together, we'll get the full perimeter, so that's 22 centimetres. So to summarise, the perimeter of a shape is the distance all the way around the outside, and we get this by adding the lengths of all the sides together. Here's one for you to try. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. Here's another one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another question for you to try. Press pause and have a go at this one. When you're ready, press play. The important thing to remember here is that a square has got 4 equal sides. 12 divided by 4 is 3, so each side of the square must be 3 centimetres long. So my square, as a sketch, looks like this. Here's a harder question for you to try. Make sure you think carefully about this one. Press pause and have a go. When you're ready, press play. Here's the answer. The trick to this one is to realise that you've got an equilateral triangle cut from a square. So if this is 4.5, so is this and this because they're 3 sides of the square. Then this distance here is also 4.5, so is this and this because these are the 3 sides of the equilateral triangle. Once I've done this, I can work out the perimeter by adding all the sides together. Here's a more difficult question for you to try now. Press pause and have a go. When you're ready, press play. The first thing you should have done is worked out that each of these parts is 1 centimetre long. Then, these parts here are 5 centimetres long each. Now it's really tempting to say that this is 5 centimetres as well, but it's not because part of it is inside the shape. You need to work out how much it's gone into the shape. Because these 2 blocks are meeting in the middle here, and this is 1 centimetre wide, we know that this is half a centimetre and this is half a centimetre. So the part sticking out here is actually only 4.5 centimetres. We have the same here, here, and here. And adding all these numbers together gives me an answer of 42 centimetres. I'm being asked to find the area of this rectangle. What it's actually asking me is how many square centimetres will fit inside it. This is a square centimetre, and if I want, I can draw square centimetres into the rectangle. Counting them gives me an answer of 15 centimetres squared. But I don't want to have to draw centimetres and count them every time I want to find the area. However, you might have noticed that if I get 5 and times it by 3, I get 15. So we can use this as a formula. So the area of any rectangle is given by the length multiplied by the width. So for this question, my formula is that area equals length times width. I can just write it like this. The length is 11 and the width is 4. So the answer is 44, and I need units as well. They're centimetres squared. This type of question would appear on the calculator paper. We do it in the same way. Area is length times width. So that's 7.3 for the length times a width of 2.8. I can do this using a calculator and I get an answer of 20.44. Again, the units are centimetres squared. Here are some for you to try. Do question A without a calculator, but you can use a calculator for B and C. Press pause and have a go. When you're ready, press play. Here are the answers. Here's a different type of question now. This time I'm told that the rectangle has an area of 54 centimetres squared. I'm told the length, that's 9 centimetres, and I want to work out the width. So this is what I want to work out. I'm going to do this using my formula. So I know that the area is the length times the width. Now I'm told the area is 54, so I can put that in. And I know that the length is 9, so I can put that in. I don't know the width yet, so I can just leave that as a W. Now, I need to work out what number I multiply by 9 to get 54. And to do this, what I can actually do is divide 54 by 9. 54 divided by 9 is 6, so the width must be 6 centimetres. To check my work, I've just said that the width is 6 centimetres. Let's work out the area. The length is 9, the width is 6, and if I multiply these together, I do get 54, which is what I was given in the question, so I know that I've got the right width here. Here are two for you to try. Do the first one without a calculator, but you can do B with a calculator. Press pause and have a go. When you're ready, press play. Here are the answers. I want to find the area of this shape here. If I look carefully at it, I can see that it's actually made up from two rectangles, and I can draw that on like this. Now I want to find the area of this rectangle and the area of this rectangle, and then add them together. For this one here, I know that this side is 10 centimetres long, and I need to find how long this is. Overall, this is 16, and this part, which is the same as this, is 12, so I know that the part that's left here is 4. So for the area of this, I've got 10 times 4, and that's 40. Now I need to do the area of this one. I can see that this is 12, and this is 6. So I want to do 12 times 6, and that's 72. Now for the total area, I've got 72 plus 40, which is 112 centimetres squared. Just out of interest, I chose to split it with a vertical line, but if you do a horizontal line, you'll get different working out, but you'll still get the same answer. And finally, just to show how creative you can sometimes be in maths, some people might like to do a large rectangle, which would be 16 times 10, and a small rectangle, which would be 12 times 4, and then subtract to get the L shape that's left over. Here's one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Whichever method you choose to use, you should still get 63 centimetres squared. To find the area of any triangle, you need to know the base and the height. These two measurements will always be perpendicular to one another. That means at a right angle. You need to be able to identify the base and the height, no matter which way up your triangle is. So for example, here, this is the base, and this is the height. On this one, this is the base, this is the height, and so on. Once you know the base and the height, it's easy to work out the area of the triangle once you realise that we can draw a rectangle around any triangle. We know that the area of the rectangle is the base multiplied by the height. If we draw on this line, we can then see that this section here is the same size as this section here, and this section here is the same size as this section here. From this, we can see that the triangle is exactly half of the rectangle. So the area of the triangle is given by the base times the height divided by 2. This formula for the area of a triangle is more commonly written like this, or this, or this. These three all mean the same thing. Each time we're doing half of the base times the height. Throughout this clip, I'll be using this version. It's really important that you memorize one of these for yourself because this formula is not given to you on the exam. So to find the area of this triangle here, I start with the formula. I then substitute in the values for the base and the height. The base is 9 and the height is 7. And now I can work this out. 9 times 7 is 63, and if I divide that by 2, I get 31.5. The units are centimetres squared. In the same way, we start with the formula, substitute in the values. The base is 12.4 and the height is 5.2. And for this one, I would be allowed to use a calculator, so I type this in as 12.4 times 5.2 divided by 2. The answer I get is 32.24 and the units are centimetres squared. Here are some questions for you to try. Do A without a calculator and B with a calculator. Press pause and have a go. When you're ready, press play. Here are the answers. In this question, I'm being given the area of the triangle and I need to find the missing side here. I can turn this into an easier question if I draw the rectangle around the triangle. Remember, the area of the rectangle is double the area of the triangle, so the area of the rectangle will be 90. So I know that 90 is going to be 9 times my missing side. And it's easy to see that the missing side will be 10 centimetres long. This one is a bit more difficult, but you would be allowed a calculator for this one. Start in the same way by drawing in the rectangle. Remember, the area of the rectangle will be double the area of the triangle, so I need to double this number. I can use my calculator for this. So we've got 2 times 29.67, and that's 59.34. Now we know that 59.34 must be 6.9 times by the missing side. This time it's not as easy to tell the answer, but we can get it by dividing. So using the calculator, we're going to do 59.34 divided by 6.9. The answer we get is 8.6. So the height of the triangle is 8.6 centimetres. Here are 2 of those for you to try. Do A without a calculator, but you can use a calculator for B. Press pause and have a go. When you're ready, press play. Here are the answers. Now for this question, I can see that the shape is made from a rectangle and a triangle. Starting with the rectangle, that's 20 by 5. So I've got 20 times 5, which is 100. Now for the triangle, this part here is 20 take away 11, so that's 9 centimetres. And this part here is 9 take away 5, so that's 4 centimetres. Now to find the area of a triangle, remember it's base times height divided by 2. So I've got 9 times 4 divided by 2. 9 times 4 is 36, and if I divide that by 2, I get 18. So this area here is 18. So the total area is 100 plus 18, which is 118 centimetres squared. Here are 2 for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. Finally, here's a more difficult exam-style question for you to try. Personally, for this one, I would find the area of the outer rectangle and then take away the area of this triangle here and this triangle here to get the area of the yellow shaded section. Press pause and have a go. When you're ready, press play. Here's the answer. The rectangle is 24 centimetres by 20 centimetres, so the area of the rectangle is 480. The area of this triangle is 18, using the formula for the area of a triangle, and the area for this one is 60. 18 plus 60 is 78, and I can then take this off the 480 to get the yellow area. We know that the area of a rectangle is the base multiplied by the height. If we start with a rectangle like this and push it over a little bit, we make a parallelogram. It doesn't matter how much we push it over. You'll notice that the base and the height always remained the same. We show that a shape is a parallelogram by putting these markings on. These mean that these two sides are parallel, and these mean that these two sides are parallel. If we draw this line here, we can take this section and put it over here. You should notice now that we're back to our original rectangle, and we know that the area of the rectangle is the base multiplied by the height. So the parallelogram must have the same area. So the formula for the area of the parallelogram is the base multiplied by the perpendicular height. So if I want to find the area of this parallelogram, I know that it's given by the base times the height. The base is 12, and the height is 5. 12 multiplied by 5 is 60, so the area is 60 centimetres squared. Here's one for you to try. Press pause and have a go. When you're ready, press play. So remember, the area is the base times the height. The base is 20 and the height is 7, and 20 times 7 is 140. The units are centimetres squared. A trapezium is a four-sided shape with a pair of parallel sides. The parallel sides are usually referred to as A and B, and the height of the trapezium is h. This is the formula for finding the area of a trapezium. I'm now going to show you where this comes from. Let's copy our original trapezium so we've got an identical one here. Now I've flipped it upside down, and if I move it along a bit, you can see that it slots perfectly into this one to create a parallelogram. Now we know how to find the area of a parallelogram. It's the base times the height. The base of this parallelogram is A plus B. So the formula for the area of the parallelogram is A plus B times by H. Remember though, we don't want the area of the parallelogram, we're looking for the area of the trapezium, which is exactly half of the picture. So we've got the A plus B times by the height halved. This is more often written as half A plus B H. So now you know where the formula for the area of a trapezium comes from. So to find this area, I start with the formula. I've got an invisible time sign here, and I substitute in A, B and H. So I've got a half times, A is 13, B is 7, and H is 6. Now I use BODMAS, so I do the brackets first. 13 plus 7 is 20. So I've got a half times 20 times 6. A half times 20 is 10 times 6 is 60. So the area is 60 centimetres squared. If this question was on a calculator paper, I could get the answer from this line here by typing in 0.5 times 13 plus 7 times 6, remembering to put the brackets in. Here are some questions for you to try. Do A and B without a calculator, but you can use a calculator for C. Press pause and have a go. When you're ready, press play. Here are the answers. When we're looking at length, the first units that we commonly use are millimetres. Then the next ones are centimetres. There are 10 millimetres in a centimetre. Because of this, if we want to change from millimetres to centimetres, we divide by 10, and if we want to change from centimetres to millimetres, we multiply by 10. For example, if I was told that something was 33 millimetres long, to change it to centimetres, I would divide by 10, and that would give me 3.3 centimetres. The next metric unit for length is metres. There are 100 centimetres in a metre. So to change from centimetres to metres, we divide by 100, and to change from metres to centimetres, we multiply by 100. So for example, if I was told that something was 4 metres long, and I wanted to know how long it was in centimetres, I would multiply by 100 and get 400 centimetres. Largest metric unit for length in common usage is the kilometre. There are 1,000 metres in a kilometre. So to get from metres to kilometres, we divide by 1,000, and to get from kilometres to metres, we multiply by 1,000. Now use these conversions to answer these questions. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. When we're looking at metric units for mass, we have grams, then kilograms, and there are 1,000 grams in a kilogram, and then tons, and there are 1,000 kilograms in a metric ton. Now try using these conversions here to answer these questions. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. And the metric units for volume are centimetres cubed, sometimes also called cubic centimetres, and litres. There are 1,000 centimetres cubed in a litre. Now try using these conversions to answer these two questions. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Here's a difficult exam-style question for you now. We're told that there are slabs which are 60 centimetres by 60 centimetres. So our little slabs look something like this. Ben wants to lay a patio in this area, but these are given in metres. So the first thing I suggest you do is change these to centimetres. Now this is a non-calculator question, so once you've done that, try and think of a practical way of fitting the slabs into the patio to work out how many slabs you need. Press pause and have a go. When you're ready, press play. Here's the answer. To get this, I converted the 3 metres and the 3.6 metres to centimetres. Now, if I had a calculator, I could multiply these two together to get the total area, find the area of a slab, and then divide to see how many fit. But because I didn't have a calculator, I didn't fancy doing that. So I worked out that I could fit 5 slabs this way and 6 slabs this way. 5 times 6 is 30. So Ben needs 30 slabs and he's got 32 slabs. So yes, he's definitely got enough. Here's your final exam-style question to try. Press pause and have a go. When you're ready for the answer, press play. To convert centimetres cubed to litres, we divide by 1,000 and we get this. But the question asks for the volume to the nearest litre, so we need to round it off to 25 litres. In this clip, we're going to be looking at solving problems on coordinate axes. In this first question, I'm told that the points A, B and C are 3 corners of a rectangle, and I want to find the coordinates of the 4th corner. To do this, I've got to see where the rectangle is going to be on this picture. So I start by joining point A to B and then to C, and now I'm looking to see where the 4th corner will be to actually make a rectangle. It's going to have to be here. Let's just double check that. Yes, that's definitely a rectangle, so this is D, and the coordinates of this are 1, 3. Here's one of those for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Now this question's very similar, but this time I'm told that A, B and C are 3 corners of a parallelogram ABCD, and I want to find the 4th corner. I'm going to start by joining these together in the same way as before, so A to B and then B to C. Now for a parallelogram, I know the base has got to be the same length as this. This is 4 squares long, so I'm going to go 4 squares along here. So I think this is where the 4th corner is. Let's just check by joining it up. This should be parallel to this, and it is. So this is definitely D, and the coordinates of this are -3, 0. Here's one of those for you to try. Press pause and have a go. When you're ready, press play. Now remember, the first thing is to join the coordinates in the right order. I've got to go from A to B and then B to C. You might be tempted when you first look at it to put a point here, but you can't do that because you would be going A, B, D, C. Instead, this is the right answer. Here's another question for you to try. Press pause and have a go. When you're ready, press play. Here are the most common answers that people give for this question. You just need 2 of these. Now there are other points as well. For example, you could have this point here, which is 4.55, or this point here, which is 7.55. As long as the y-coordinate is 5, then your answer is actually correct. Here's another question for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. We know that ABC is an isosceles triangle because AC is the same length as AB. Here's another question for you to try. Press pause and have a go. When you're ready, press play. You could make a parallelogram here, or here, or here. So these 3 green crosses mark the 3 possible answers. You need to write down 2 of them. I want to find the surface area of this cuboid. To do that, I need to find the area of each individual surface and then add them all together. There are 6 surfaces in total on this cuboid. If I draw in these dotted lines, I can then clearly see the 6 surfaces. I've got a front and a back, and they're the same. I've got a top and a bottom, and they're the same. And I've got a right-hand side and a left-hand side, and they're the same. All 6 surfaces are rectangles, so to calculate the area, I just need to do the length multiplied by the width for each one. So let's start with the bottom. The length is 7 and the width is 2, so I've got 7 times 2, which is 14. The top is the same as the bottom, so the top is also 14. Now let's do the right-hand side. It's 2 by 4, and that's 8. The left-hand side must be exactly the same, so that's 8 as well. Now I want to do the front. Now for the front, I can see that the length is 7 and I need to know the height. But this line here will be the same as this one here, so the height is actually 4. So I've got 7 times 4, which is 28, and the back will be the same as well. So that's 28 too. So to get the total surface area, I need to add all of these together, and I get 100 centimetres squared. The units are centimetres squared because remember we were looking for an area and all of the lengths were in centimetres. Here's one of those for you to try now. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. In this question, I'm being asked to find the surface area of this triangular prism. The surfaces on this triangular prism are all either triangles or rectangles. So before we continue with this clip, we need to review how we find the area of a rectangle and the area of a triangle. So the area of a rectangle is really straightforward. It's the length multiplied by the width. And for the area of a triangle, we have the base multiplied by the height and then divided by 2. Press pause and have a go at finding the area of these 2 shapes. When you're ready, press play. Here are the 2 answers that you should have got. We can now use these 2 formulas to help us find the surface area of the original triangular prism. So here it is again. The first thing I'm going to do is draw on some dotted lines to show all the different surfaces. like this. I can now see that I've got a triangle at the front and an identical one at the back, a rectangle at the base, a rectangle at the right-hand side, and a rectangular slope. I need to find the area of each of these and then add them together to get the total surface area. So I'm going to start with the front triangle because that's probably the hardest bit. The base is 12, the height is 5, and remember I've got to divide that by 2. I get 30. The back triangle is identical, so the back is also 30. Now I'm going to do the base. The base is a rectangle and it's 12 by 4. So that's 48. Now I'm going to do the right-hand side. This is a rectangle and it's 5 by this length here, which is 4 because it's the same as this one here. So I've got 5 by 4, which is 20. The last area is the area of the slope, and that is a rectangle which is 13 by 4. And that gives me 52. So to find the total, I add all of these together and I get 180 centimetres squared. Here's one of those for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Now this is a harder question. I'm still being asked to find the surface area of a triangular prism, and the cross-section is an isosceles triangle. So I need to find the area of the front. To do that, I need the base of the triangle and the height of the triangle, but I don't know the height. If I draw it in though, I can see that I've just made a right-angled triangle over here. I know that the hypotenuse of the right-angled triangle is 25, and that the base of the right-angled triangle is 24, because it's exactly half of this 48. Now I just need to find this side. So I'm going to actually use Pythagoras to do this. So I start with 25 squared, which is 625. Then I have 24 squared, which is 576. Because I'm not finding the longest side, I'm going to take away, and I get 49. Square rooting this gives me 7. So I know that the height of the triangle here is 7 centimetres. So I've now got all the information that I need to be able to find the surface area. I'm going to draw in some dotted lines to show myself all the different surfaces. So I can see I've got an isosceles triangle for the front and an identical one for the back, a rectangle for the base, and a rectangle for the side here, and one exactly the same for the side here. So I'm going to start with the triangle at the front. The base of this is 48 and the height is 7. So I've got 48 times 7 and I need to divide that by 2 because it's a triangle. This gives me 168. The triangle at the back is identical, so that's also 168. For the base, I have 48 multiplied by 3. So that's 144. For the slope on the left-hand side, I can see that the length is 25 and the width is 3 because it's the same as this. So for the slope on the left, I've got 25 times 3, which is 75. Now the slope on the right is identical to the one on the left because this side is the same length as this side. so the slope on the right has an area of 75. Now I can add all the parts together to get the total, and I get 630 centimetres squared. Here's one of those for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. I want to find the volume of this cube. Because it's a 1 by 1 by 1 cube, we say that the volume is 1 cubic centimetre. We can write this as 1 centimetre cubed. To find the volume of this cube, I could split it up like this. I can now see that here I've got 4 of these cubes, and here I've got another 4. So I've got 8 centimetres cubed altogether. A quicker way to find the volume is to say that the length here is 2 centimetres, the width is 2 centimetres, and the height here is also 2 centimetres. To find the volume, I multiply these 3 dimensions together. 2 times 2 is 4, times 2 is 8. So you can see I get 8 centimetre cubed again. Now this isn't a cube, it's a cuboid, but we can find the volume in the same way. Let's start by splitting it up. We can see that we've got 4, 8, 12 of these, so the volume is 12 centimetres cubed. The faster way is to find the length, width and height. Now to find the volume, we can multiply these together. So we've got 3 times 2 times 2. 3 times 2 is 6, times 2 is 12, so the volume is 12 centimetres cubed. Now here's one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Now using our technique, we can find the volumes of cuboids even when we can't see all the individual cubes. Remember, the volume is the length, that's 6, times the width, that's 3.5, times the height, that's 2. You can use a calculator to help you with this. The answer is 42 centimetres cubed. If this question came up on a non-calculator paper, it helps to remember that you can do multiplication in any order. So instead of trying to do it this way, I would do 2 times 3.5, which is 7, and then times that by 6 to get the 42. Here are some questions for you to try now. You can use a calculator for these. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. In this slightly different type of question, I'm told that the volume of the cuboid is 140 centimetres cubed, but part of the image has been blurred, so I need to work out the length. Remember that the formula for the volume is the length times the width times the height. Now I know that the volume is 140, so I can put this in straight away. I'm trying to calculate the length, so I'm going to leave that as an L. I can find the width by looking at the picture. The width is 7. I can find the height in the same way. Looking at the picture, I can see that the height is 2. So I have 140 equals the length times by 7 times 2, which is 14. Now I can work out the length. 10 times 14 would give me 140, so the length must be 10 centimetres. If you can't see it from this stage as easily as I can, you can always do it by dividing the volume by this number here. 140 divided by 14 still gives me 10 centimetres for the length. Here are some questions for you to try. Use a calculator to help you with these. Press pause and have a go. When you're ready, press play. Here are the answers. These are all words associated with circles, and you need to know what each of them is. So, obviously, we know what a circle is. The centre of the circle is the exact middle of it. Now, a radius is any line that goes from the centre to the edge of the circle. So this is a radius, so is this, and this, and this. A diameter is a line that goes across the circle through the centre from one side to the other. For a chord, do any 2 points on the circle, like this, and then join them together. Finally, the circumference of a circle is the distance around the outside of it. Make sure you know and understand all of these terms. Now, here are some questions for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Obviously, your picture might not look identical to mine, but as long as you've used the definitions correctly, it should be fine. In this question, I'm being asked to work out the area of this circle. You need to know that the formula for the area of a circle is pi r squared. Now, pi is just a number. It's 3.142. R means the radius of the circle. That's the distance from the centre to the circumference. There's an invisible time sign here. You need to memorise this formula. It won't be given to you on the exam paper. To find the area, we substitute in the values for pi and r. So pi is 3.142. We've got the invisible time sign, and r is 8 for this circle, and that's squared. We can use a calculator now to work this out, and the answer we get is 201.088. The question asks me to give my answer to 2 decimal places. So I have 201.09, and the units are centimetres squared. Here's one for you to try. You can use a calculator to do it. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. Remember, the radius is the distance from the centre to the circumference. Press pause and have a go. When you're ready, press play. So you start with the formula. Remember your invisible time sign. Pi is 3.142. And then we need the radius of the circle. This is the diameter of the circle. The radius is just from the centre to the circumference, so the radius will be half of 18, which is 9. So we have 9 squared. Using a calculator, we get 254.502, and then rounding, we get 254.50 centimetres squared. Here's another one for you to try. This time you've got a semicircle, which of course is exactly half of a circle. Press pause and have a go. When you're ready, press play. Here's the answer. You'll notice I've shown you two ways of getting this. The first way is to imagine the whole circle and work out the area of that. Remember that the radius is 12. So this here is the area of the whole circle. To find the area of the semicircle, I need to halve it, and I get this answer to 2 decimal places. The other way is to realise that the area of a semicircle must be given by the formula for the area of a circle divided by 2. We can use this new formula and substitute in the values to get the answer in a slightly quicker way. Here are some more for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Here's an exam-style question for you to try now. You want to find the area of the path around the pond. To do this, you want to find the area of the largest circle and then take away the area of the smaller circle. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another question for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. The key to getting this right is to realise that if the circle fits exactly inside the square, then it must have a radius of 5 metres. This is a non-calculator question on the area of a circle. It tells me to give my answer in terms of pi. This bit looks really confusing, but it's actually quite straightforward to do. We still need the formula. We know that it's pi r squared. And we have an invisible time sign. Now this time, instead of substituting in the number 3.142 for pi, I'm just going to leave the pi symbol there. I'm multiplying this by r, which is 7, squared. So I get pi times 7 squared, which is 49. I can rewrite this as 49 pi, and this is my answer. So the area of this circle is 49 pi centimetres squared. I haven't had to use a calculator, and I've left my answer in terms of pi. Here's one for you to try now. Do this question without a calculator. Press pause and have a go. When you're ready, press play. Here's the answer. Here's your final question. Do this one without a calculator. Press pause and have a go. When you're ready, press play. Whoops! I forgot to tell you that this is a really hard question, but I'm sure you worked that out for yourself. Here's the answer. In this clip, we're going to look at how to calculate the circumference of a circle. The circumference is the distance around the outside of the circle, and the formula for it is 2 pi r. Pi is just a number. It's 3.142. R is the radius of the circle. That's the distance from the centre to the edge. In the formula, there's an invisible time sign here and here. You need to memorise this formula. It won't be given to you on the exam paper. So let's say I was told that the radius of this circle is 8 centimetres. So to calculate the circumference, I start with the formula. Remember, there's an invisible time sign here and here. Now I can substitute in the values for pi and r. So I've got 2 times pi, which is 3.142, times r, which is 8. I can use a calculator to get the answer, and it's 50.272. The units are centimetres, because the circumference is just the distance around the outside. Here are two for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Just out of interest, in questions where you're given the diameter of the circle, like this one here, it's quicker to just multiply pi by the diameter. You'll get the same answer. Here's another question for you to try. This time you're being asked to calculate the perimeter of this semicircle. Perimeter means the distance all the way around the outside, so you've got a curved part and a straight part. Remember that a semicircle is exactly half of a circle. Press pause and have a go. When you're ready, press play. Here's the answer. To get this, I realised that the curved part was exactly half of the circumference of a circle. That's given by 2 pi r, so I divide it by 2 to get this part here. This is the total for the curved part. The straight part is 14, and we add them together to get the perimeter. Here's a difficult exam-style question for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. In this question, I'm being asked to work out the surface area of this cylinder. To help me to do this, I'm going to think about the net of a cylinder. The net of a cylinder is made up of two circles for the top and the bottom, and then a rectangle which is wrapped around to create the curved surface area. So I know that the radius of this circle here must match this, so that's 5 centimetres, and that the height of the rectangle here must match this, so that's 20 centimetres. Obviously, this circle at the bottom is exactly the same as this one at the top. With what I've got so far, I can work out the area of this circle and of this circle, but I can't work out the area of the rectangle because whilst I know the height, I don't know the length. The important thing to realise is that the length here must be exactly the same as the circumference of the circle. So if I can work out the circumference of the circle, then I will know the length of the rectangle. So the first thing I'm going to do is work out the circumference of the circle. I know that circumference is given by the formula 2 pi r. So that's 2 times pi times the radius of the circle, which is 5. I use the pi button on my calculator for this, and I get the answer 31.41592654. I'm not going to round this off yet, I'm only going to round at the very end. And this, of course, is a circumference, so it's centimetres. So now I know that the length of the rectangle is this number here. So I can work out the area of the rectangle. That's going to be this number here, 31.41592654, multiplied by the height, which is 20. And that gives me 628.3185307 centimetres squared. Now I need the area of the circles. Each of these circles is the same, so I'm going to just work out the area of one of them and then multiply it by 2. Remember, the area of a circle is given by pi r squared. So that's going to be pi multiplied by 5 squared. Again, I'm going to use the pi button on my calculator for this. This gives me 78.53981634, and that's centimetre squared again. So for the surface area, I need 2 of these circles plus the area of the rectangle. So this number multiplied by 2 is 157.079637, and I want to add on 628.318 5307. I get the final answer, 785.4 centimetres squared. And now I've rounded to one decimal place. Here's a question for you to try now. Remember to use the pi button on your calculator. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. The important thing to notice in this question is that you're given the diameter of the circle. From this, you can work out that the radius is 11, and you use that 11 here and here. A prism is a three-dimensional shape that has the same cross-section all the way through. These are all prisms. Let's just have a look at this middle one here. The cross-section of this is this triangle here. If I put this into a bacon slicer and took lots of very thin slices, they would all be this same triangle. Now, when I'm trying to find the volume of a prism, I always follow exactly 3 steps. Step 1 is to shade in the cross-section. So, on this cuboid, I'm going to shade in this part here, which we can see is a rectangle. On this triangular prism, I'm going to shade in this, which is a triangle. And on the cylinder, I shade in this, which is a circle. For step 2, I need to find the area of the cross-section. This one is a rectangle, so the area will be the length times the width. This is a triangle, so the area will be the base times the height divided by 2. And for this one we have a circle, so the area is pi r squared. And for the third step, I need to multiply the area that I've just found by the length of the prism. So on this one, the length is this distance here, so the volume is the area multiplied by the length. On this one, the length is this distance here, and again the volume is the area multiplied by the length. And on the cylinder, the length is this distance here, so again the volume is the area multiplied by the length. Now let's put that into practice. So to find the volume of this cuboid, step 1 is to shade in the cross-section. Step 2 is to find the area of the cross-section, and that's going to be 7 times 2. And that's 14. Step 3 is to multiply the area by the length. So the area is the 14 that I've just found, and the length is 8 centimetres. 14 times 8 gives me 112, and my units are centimetres cubed. For the triangular prism, step 1, shade in the cross-section. The area is the base, which is 6, multiplied by the height, which is 9, and then divided by 2, and that gives me 27. So the volume is the area I've just found multiplied by the length. The area is 27, and the length is this here, which is 4. So my answer is 108, and again it's centimetres cubed. On the last one, the cross-section is a circle, so that's step 1. For step 2, I need the area. The formula is pi r squared, and it tells me to use 3.142 for pi. So I've got 3.142 multiplied by the radius squared. Now the radius is the distance from the centre of the circle to the edge, so that's actually 6.5. I use a calculator for this bit, and I get 132.5 132.7495. For the volume, I have the area multiplied by the length. The area is 132.7495, and the length is this here, 7.5. Again, using a calculator, I get 995.62125 centimetres cubed. On an exam, you'll usually be told the degree of accuracy that you need to round this off to. Here are 3 for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Here's a more difficult question for you to try. You're still going to use the same 3 steps. You need to start by shading in the cross-section. That's this part here. Once you've found this area, you then multiply this by the length of the prism. Press pause and have a go. When you're ready, press play. Here's the answer. Now this is a really difficult looking question, but it's made easier when you realise that this handle here is actually not part of the question. And if you mentally move it out of the way, you're left with just a cylinder. Once you've found the volume in centimetres cubed, you then need to change it to litres. The conversion for that is here. Press pause and have a go. When you're ready for the answer, press play. Here's the answer, together with all of the working. Before we start to look at angles on parallel lines, you need to remember this, that the angles on a straight line will always add up to 180 degrees. So for example, if I'm told that this angle here is 140 degrees, then I know that this one here must be 40 degrees. You'll be using this throughout the clip. These 2 marks here tell us that these lines are parallel lines. They're never going to meet. If we draw a line across a pair of parallel lines, we create angles. You need to learn to spot 3 different letters in the shapes formed by these lines. The first letter I can look for is a letter X. You should be able to spot that there's one here. When we have an X shape, this angle will be equal to this angle. These are called vertically opposite angles. There's also another pair. This angle will be equal to this angle. And again, these are called vertically opposite angles. Here's another X shape. We have a pair of vertically opposite angles here, and another pair here. So, for example, if I was told that this angle is 50 degrees, then I know that this angle is also 50 degrees, and the reason is that they are vertically opposite angles. The next letter you're looking for is an F shape. The first one is here. Whenever you get an F shape, this angle will be equal to this angle. These are called corresponding angles. There's a backwards F here. This angle will be the same as this one. Remember, they're corresponding angles. There's an upside down F here. Again, these are corresponding angles. And finally, there's one more F shape here with another pair of corresponding angles. So if I was told that this angle was 60 degrees, then I know that this angle is also 60 degrees, and the reason I can give is that they're corresponding angles. The last letter shape that you're looking for is a Z. The first Z shape is here. this is still a Z even though it's been stretched out a bit. This angle is equal to this angle. These are called alternate angles. Here's another Z shape. This time it's backwards. We can see that there's alternate angles here and here. So, if I was told that this angle here was 130 degrees, then I know that this angle here is also 130 degrees, and the reason is because they are alternate angles. Here's a question for you to try. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. Here's another one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Here's a slightly more difficult exam-style question for you. For the second part, notice that it says give reasons for your answer. This is a clue that you're going to have to write down more than one thing. Press pause and have a go. When you're ready, press play. The answer for the size of the angle marked Y is 113 degrees. There are lots of different ways to get this answer, so how you've got it will affect what reasons you've written down. This is the way I found the angle. I noticed that up here, the angle I'm looking for is on a straight line with this angle here, so they must add up to 180. This angle here is inside an F shape with this one here, so these two are corresponding. That tells me that this is 67 degrees, and then this must be 113 degrees to make 180. So my reasons are that I used a pair of corresponding angles, and I used the fact that angles on a straight line add up to 180 degrees. Another way of getting this answer would be to spot that Y is on a straight line with this angle here, and this angle is in a Z shape with the 67 degrees. So these are alternate angles, and that's 67 degrees, and then these add up to 180, so that's 113 degrees. For this method, your reasons would be that I used a pair of alternate angles and the fact that angles on a straight line add up to 180 degrees. I've just shown you two ways of getting this answer. There are actually other ways as well, but your reasons will always be that the angles on a straight line add up to 180 degrees, and that you've either used corresponding angles or alternate angles. Here's another question for you to try. Press pause and have a go. When you're ready, press play. Here's the answer, and again, you can either write these reasons or these reasons. Here's your final question. Press pause and have a go. When you're ready, press play. Here's the answer. The way I found this was that I spotted the F shape here, so I knew that this and this were corresponding, and then here I have the angles on a straight line, and these must add up to 180 degrees. Remember that this square corner here is telling you that it's a right angle of 90 degrees. Before we begin to look at the angles in a triangle, there's one thing that you need to revise. The angles on a straight line will always add up to 180 degrees. Now, the angles inside a triangle also add up to 180 degrees. For example, if I was told that this angle here is 60 degrees, and this one here is 70 degrees, I can then work out the size of this one. 60 add 70 is 130, so I need another 50 degrees to get to 180. So to find the size of angle X in this triangle here, I first of all need to add these two together. So 1 and 2 is 3, and 7 and 4 is 11. So this adds up to 113. To find the size of this angle now, I need to take this away from 180. 0 take away 3 doesn't work, so we borrow. 10 take away 3 is 7. 7 take away 1 is 6, and 1 take away 1 is 0. So the size of the missing angle is 67 degrees. To find the size of angle Y, I need to know the sizes of the other two angles inside the triangle. For this one here, I've got a straight line, so I know that these two add up to 180. I can see quite quickly that that means that this is 70 degrees. I have the same situation over here. These two angles are on a straight line, so they must make 180, so this one is 60 degrees. Now remember, the angles inside the triangle must add up to 180. 70 add 60 is 130, so the missing angle at the top here must be 50 degrees. Here are some for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. I want to find this angle here. I know that the three angles inside a triangle add up to 180, but I'm missing this angle here. If I can find this, then I can find this. Now, whenever I see these parallel signs, I know that I can look for letter X's, F's, or Z's. And looking at this, I can see a letter Z. So I know that this angle is the same as this one. It's 55 degrees. And that's because these are alternate angles. I write this down as my first reason. Now I'm going to focus on the triangle. I've got 63 and 55, so I'm going to add those up. 3 and 5 is 8, and 6 and 5 is 11. So I've got 118 degrees so far. I can take this off 180. 0 take away 8 doesn't work, so we borrow. 10 take away 8 is 2, and 7 take away 1 is 6, and 1 take away 1 is 0. So the missing angle must be 62 degrees. The second reason I need to write down is that the angles in a triangle add up to 180 degrees. So my final answer is that angle X equals 62 degrees, and these are my reasons. Here's a question for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Angle X is 80 degrees because we've got an X shape here, so these are vertically opposite angles. Angle Y is 50 degrees because we've got a Z shape here, so these are alternate angles. To find angle Z, we know that the three angles inside the triangle add up to 180. We know that X is 80 and Y is 50. So Z must be 50 to make a total of 180. Here's another slightly harder question for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. To find X, I spotted an F shape here, so I've got a pair of corresponding angles. Angle Y is a bit more difficult, but if you look carefully, you can see that it's inside a triangle. Inside this triangle, I've got the angle I'm looking for and this angle here, so I just need to find the value of this one. Remember, I've already worked out X. I know that that's 105 degrees. These two here must add up to 180 because they're on a straight line. So this one is 75 degrees. The three angles in the triangle must make 180. So far, I've got 145, so the third angle here must be 35 degrees. Here's one more for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. For angle A, you should have spotted an F shape here, so you've got a pair of corresponding angles. For angle B, you should have spotted a Z shape here, so you've got a pair of alternate angles. To find angle C, you could have spotted that it's inside a triangle. We know the size of angle B, that's 110 degrees. So if we can find this angle here, we can work out C. Now this angle here is in a Z shape, so we know that it's 45 degrees. So we've got 45 and 110 so far, that's 155, and if we take that away from 180, we get the value of C, which is 25 degrees. There are other ways of getting the answer for angle C. Now, in the exam, you might be asked to prove that the angles of a triangle always add up to 180 degrees. To do this, the first thing you need to do is draw any old triangle. Like this one here. I've labelled it A, B and C. It will help if you do this too. Then, draw a line here, which is parallel to this line here. Now this angle here is the same as this angle here, because they're alternate angles. We can write this by saying that this angle here is ECB, so angle ECB equals angle CBA for this angle here. We explain that these are the same because they're alternate angles. In the same way, this angle here must be equal to this angle here. Again, because they're alternate angles. We can write this as angle DCA for this one here is equal to angle CAB for this one. And again, that's because they're alternate angles. Now, I'm going to call this angle X, and because this one is the same, I can call it X as well. In a similar way, I'm going to call this one Y, and because this one's the same, I can call this Y. I've only got one angle left, that's this one here, and I'm going to call that Z. Now look what happens. At the top here, we've got a straight line. We know that the angles on straight lines add up to 180 degrees, and we've got X, Y and Z on the straight line. So, X plus Y plus Z must equal 180 degrees because they're angles on a straight line. Now if we look at the triangle, we can see that inside the triangle we've got the same three angles, X, Y and Z. Remember that X, Y and Z add up to 180, so we now know that the angles in the triangle also add up to 180. So this line here implies that the angles in a triangle add up to 180. So we've now proved that the angles in a triangle always add up to 180 degrees. In this clip, we're going to be looking at three special types of triangle. The first type is a right-angled triangle. This has a 90-degree angle. The second type is an isosceles triangle. This has two equal sides. They're shown with these two marks. The base angles of this type of triangle are also equal. It's really important that you know how to identify which are the two equal angles. They are where the two equal sides meet the third side. So here and here. These are the base angles of this isosceles triangle, and they will be equal. If the triangle is upside down, you still need to be able to find the base angles. Remember, it's where the two equal sides meet the third side, so here and here. The third type is an equilateral triangle. All the sides are equal, shown by these marks, and all the angles are equal, and they're all 60 degrees. Here's a question for you to try now. Press pause and have a go. When you're ready, press play. To find this, remember that this angle here is 90 degrees. So we have 90 plus 39. 0 and 9 is 9, and 9 and 3 is 12. So far we've got 129 degrees. In the triangle altogether, there must be 180 degrees. So if we take off the 129, 0 take away 9 doesn't work, so borrow, 10 take away 9 is 1, 7 take away 2 is 5, and 1 take away 1 is nothing, we get 51 degrees. So the size of angle X is 51 degrees. Here are two more for you to try. This time, as well as finding the size of the angle, you need to give reasons. Press pause and have a go. When you're ready, press play. Here are the answers with the reasons. To find angle X, I spotted that these two were the base angles of an isosceles triangle, so they must be equal. I found what they added up to, which was 116, and took it away from 180 to get the third angle. To find angle Y, I noticed that these two were the base angles of the isosceles triangle, so I took this away from 180 to get 144, and then I know that these two add up to 144, and they're the same as each other, so I split 144 in half to get the answer 72 degrees. Here are some more questions for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. Here's your final difficult exam-style question. Press pause and have a go at this one. When you're ready, press play. Here's the answer. The word polygon means many angles. These are examples of irregular polygons. Let's focus on one of them. Here I've got an irregular heptagon. That's a 7-sided shape. I want to work out the sum of the interior angles of this heptagon. What that means is the sizes of all of these angles added together. To do this, I choose any corner of the heptagon. I'm going to choose this one here. And I use straight lines to join it to every other corner. So you can see it's already joined to this one. I need to join it to this one here, then this one as well, this one, and it's already joined to this one. I'm just going to neaten this up a bit. Now you should be able to see that inside my heptagon I've made 5 triangles. I know that the angles inside a triangle add up to 180 degrees. So because I've got 5 of them, inside this heptagon I must have 5 times 180. And 5 times 180 is 900. So the sum of the interior angles of this heptagon is 900 degrees. Here's one for you to try. This time you want to work out the sum of the interior angles of an irregular nonagon, which is a 9-sided shape. You'll find it helpful to sketch any 9-sided shape to help you with this. press pause and have a go. When you're ready, press play. Here's the answer. Just out of interest, did you notice that when I did a 7-sided shape, I got 5 triangles, and you've just done a 9-sided shape, and you should have got 7 triangles. The number of triangles is always 2 less than the number of sides. So you should now be able to do this question without a sketch, as long as you know how many sides an octagon has. Press pause and have a go. When you're ready, press play. Here's the answer. An octagon has 8 sides. 2 less than this is 6, so you're looking at 6 triangles, and 6 times 180 is 1080. Now in this question, I'm being asked to work out the size of one interior angle of this regular hexagon. In a regular hexagon or any regular shape, all of the angles are the same size. So to find the size of one angle, what I'm going to do is find the sum of all the interior angles of the hexagon and then divide by 6, because there are 6 equal angles. So 6 sides tells me that I'll have 4 triangles. So I want 4 times 180, and that's 720. So the sum of the interior angles is 720 degrees. Now I want to divide that 720 by 6. I've done that division as a bit of side working here, and you can see that I get the answer 120 degrees. So the size of one interior angle is 120 degrees. Here's one for you to try. Your clue for this one is that a decagon has 10 sides. Press pause and have a go. When you're ready, press play. Here's the answer. You should have realised that a decagon has 10 sides, so that's 8 triangles. 8 times 180 is 1440. Then to work out the size of one interior angle, you need to divide that by 10, because there are 10 sides and so 10 angles, and you get 144 degrees. Now I want to work out the size of one exterior angle of this regular hexagon. Before I do this, I need to know what an exterior angle actually is. To get an exterior angle, we extend any one of the sides, and the exterior angle is this angle here. We also have another exterior angle here, here, and here. I'm just going to focus on this exterior angle here, but be aware that they are all the same size. Now we've already worked out in a previous question that the interior angle of a regular hexagon is 120 degrees. So how can we work out the exterior angle? Well, at the top here we have a straight line, so it must be 180 degrees altogether. So that tells me that the exterior angle is 60 degrees. So we have a formula. One interior angle and one exterior angle will always add up to 180 degrees. Here's a question for you that covers everything we've done in this clip so far. Press pause and have a go. When you're ready, press play. Here are the answers. Here's a more challenging exam-style question for you now. Press pause and have a go. When you're ready, press play. To find the size of this angle, I first of all realised that on a square we have a right angle here, so that's 90 degrees. Then I worked out the interior angle of a regular pentagon here, that's 108. So I've got 108 here and 108 here. Now I know the angles around a point add up to 360. So to find x, I do 360 take away the two 108ths, and take away the 90. That leaves me with 54 degrees. Here's another question for you to try. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. I'm being asked to measure and write down the bearing of B from A. Whenever I see the word bearing, I know that I'm going to have a north line. North lines always go straight up the page. Bearings are always measured in a clockwise direction. I need to know where to actually put the north line. The question tells me. It says I want B from A. The from A part tells me that I want my north line from A. So my north line looks like this. I then need to draw a line joining A to B. Like this. Now I want to measure this angle here. So I get my protractor, position it like this. Now because bearings are always measured in a clockwise direction, we always use the outside scale on our protractor. We can see that this angle is 70 degrees. When we write it as a bearing, it needs to have 3 figures. If it's a 2-digit number like 70, we put an extra 0 at the front. So the bearing is 070 degrees. Here's another one. This time I want to measure and write down the bearing of B from A. Remember, this tells me where to put the north line, so it's going to go here. So here's my north line, and I now need to draw a line joining A to B. Remember, bearings are measured from north in a clockwise direction, so I'm looking to measure this angle here. This angle we can see is bigger than our protractor, so to make things a bit easier, I'm going to draw this line here. I now know that this part is 180 degrees. I'm going to measure this part here and then add it on to 180 degrees to get my total bearing. So using my protractor and putting the 0 here, I can see that this is 60 degrees. So the total bearing is 180 plus 60, which is 240 degrees. This is already 3 figures, so this answer is fine to be left as it is. Just out of interest, some of you might have spotted that I could get this answer by measuring this angle here and then taking this away from 360. The reason I didn't teach you this way is that because in an exam situation with all the pressure that's on you, some people might forget to take this away from 360. So this method is a bit risky, whereas this method will usually get you the right answer. Here's a question for you to try. You'll need to copy the points A, B and C very carefully onto some squared paper. To help you do this, this is how far apart the 3 points are. Press pause and have a go. When you're ready for the answers, press play. The bearing of B from C is 061 degrees. You are allowed answers within 2 degrees of this, so anything from 059 to 063. The bearing of A from B is 288 degrees. And again, you're allowed anything within 2 degrees of this, so anything from 286 to 290. This is another typical exam-style question. In part A, I'm asked to measure the bearing of B from A, so I want the angle from A here. I measure this using my protractor. So with my protractor in position, I can see using the outside scale that it's 51 degrees. So the bearing of B from A is 051 degrees. For the second part, I'm going to need to measure a bearing of 130 degrees from B. So that will be something like this. I can then draw a line, and I want to measure 4 centimetres along this line. So that will be something like that. Now let me do this accurately using my protractor. So my protractor is now in position, and 130 degrees is here. So I can mark this with a dot and then move the protractor out of the way. I can now draw a line from B through the dot, like this. Now I need to measure 4 centimetres along this line, and this will be where C is. So I put my ruler on, and I'm looking for 4 centimetres. That's here. So that's where C is. I mark it with a cross, and I'm sure to label it. This is my final answer. Here's one of those for you to try now. Before you begin, you need to mark the points A, B and C on a piece of plain paper. B is 11 centimetres away from A, and C is 5 centimetres away from A. Make sure that you have a right angle here. Once you've done this, you can have a go at parts A and B of the question. Press pause and try it. When you're ready for the answers, press play. For the first part, you should have just focused on this information here. You should have drawn your north line from A, and then measured a 60-degree angle, like this. Then you need to focus on this piece of information. We want a bearing of 310 degrees from B. So we have a north line from B, and if we draw this line in, we know we've got 180 degrees. Now 310 minus 180 is 130, so we want another 130 degrees. We can measure this using our protractor, like this. We now draw a line from B through that point. And where the two red lines cross is the position of the town D. I hope you remembered to label it. For part B of the question, we want to measure the bearing of town D from town C. So we need a north line at town C. We draw a line from C to D and then use a protractor. You should have got a bearing of 102 degrees. Remember, you can be 2 degrees within this, so anything from 100 to 104. In this question, I'm now being asked to work out the bearing of the lighthouse from the ship. This means that I'm not actually going to use a protractor. I can, however, draw a diagram to help me. I'm told that I've got a ship and a lighthouse, and I'm told the bearing of the ship from the lighthouse. Because of this, I start with the lighthouse. I would have a north line up here, and I want a bearing of 50 degrees. So the ship is somewhere over here. What I want to do is work out the bearing of the lighthouse from the ship. So for this, I would have a north line from the ship, and I need to work out this angle here. If I draw this line here, I now know that this angle is 180 degrees. To calculate the whole bearing, I just need to work out how big this is and add it on to 180. Because these are two north lines, I know that they're parallel, so I have angles on parallel lines. These two angles are in a Z shape, so they're alternate angles. That means that they're the same, so this angle here must be 50 degrees. So the whole bearing is 180 plus 50, which is 230 degrees. This is my final answer. Here's your final question to try. Press pause and have a go at it. When you're ready for the answer, press play. Here's the answer. In this question, we're being asked to bisect the line AB. We all know that dissect means to cut something up. Bisect means to cut it exactly in half. We're going to use a pair of compasses to do this. The first thing we need to do is put the compasses on A. We now open them out so that they're over halfway along the line. Like this. We now move the compasses to this position and draw an arc. We now repeat this below the line as well. Now we need to move the point of the compass to B, but we need to keep the compasses open exactly the same amount. Like this. Again, we draw an arc, here, and another arc, here. We've now got two curvy crosses. If we join these two crosses together using a ruler, we have bisected the line AB. Something to notice is that when you bisect a line in this way, you'll always have a perfect right angle here. Here's a question for you to try. To do this, you'll need to copy this shape really accurately onto some paper, and then use your ruler and compasses to bisect two of the sides. Press pause and have a go. When you're ready, press play. You should have bisected AC and BC. To check whether your answer is correct, for this particular triangle, your lines should cross here on the longest side of the triangle. If you really want to check how accurate you've been, you can do the following. Put your compasses on the point where the lines cross. Now open them out so that the pencil is on A, like this. If you now draw a circle, if you've been really accurate, the circle should touch B and C exactly. You can see that mine's not quite perfect. If you do it perfectly accurately, it should look like this. In this question, you're being asked to use ruler and compasses to draw a line which is equidistant from A and B. Equidistant means that it will be an equal distance away from A and B. It's quite tempting to do something like this, but this is a rubbish answer, because if I choose a point on the line here, I can see that it's closer to A than it is to B. You should be able to see that what we really want is a line that goes at an angle. Now, if we choose a point on the line, it should be the same distance from A and B, no matter where we choose the point. The way to get this answer accurately is to draw an imaginary line between A and B and then bisect it. So you're going to have a go at this now. You're going to need to draw two dots on a piece of paper. The diagram shows you how far apart they are. Once you've got your two dots, you need to draw a line which is equidistant from each of them. Press pause and have a go. When you're ready, press play. Your answer should look something like this. To check your answer, pick any 2 points on your line. Let's say here and here. Now measure this distance and this distance using a ruler, and they should be the same. You should also measure this distance and this distance using a ruler, and they should be the same as each other as well. In this question, I'm being asked to use a ruler and compasses to draw a line which is perpendicular to the line AB at the point C. Perpendicular means at right angles. So what I'm looking for is a line that goes through C like this and creates a right angle here. To do this, I'm going to use a pair of compasses. I start by putting them on the point C. I open them out a little bit. It doesn't really matter how much at this stage. Make a mark on the line here, and then keeping the compasses open exactly the same amount, make another mark the other side. Like this. The effect has been to make the point C exactly in the middle of these 2 points here. So now, if I bisect the section of the line in between these 2 points, it should go at a right angle exactly through C. So to bisect this section of the line, I start by putting the compass point here. Now need to open the compasses out a bit more so that the pencil is past C. Like this. I'm going to draw an arc here and another one here. I now need to repeat this procedure on the other side, keeping my compasses open exactly the same amount. So I move the compasses to here and draw an arc and another arc. I've now got 2 curvy crosses. If I join these together using a ruler, it goes through the point C and it creates a right angle. So the line I've drawn is perpendicular to AB at the point C. Here's a question for you to try. To do this, you're going to need to draw this line accurately onto a piece of squared paper. The distance here is 5 squares, and the distance here is 17 squares. Make sure that the line AB is the right length and that you put C at the right point on the line. Once you've drawn it out, you need to use ruler and compasses to draw a line which is perpendicular to AB at the point C. Press pause and have a go. When you're ready for the answer, press play. Here is what your answer should look like. To check that your answer is correct, measure this angle here. It should be 90 degrees. In this question, I'm asked to use ruler and compasses to draw a line perpendicular to the line AB that passes through the point C. So what I want to do is draw a line through C that makes a right angle with the line AB. I'm going to use compasses to help me do this accurately. The first thing I do is put the compasses on the point C and open them out a little bit. The amount you open them doesn't really matter. I now make a mark here and here. Once you've done this, all you need to do now is bisect this section of the line here. This is something that you should have done before. Let me quickly remind you of how we do it. Now that we've got these 2 curvy crosses, if we join them together, we'll have our perpendicular. Like this. So this is my completed perpendicular to the line AB that passes through the point C. Here's one for you to try now. You'll need to copy the line AB and the point C very carefully onto squared paper. Press pause and have a go. When you're ready, press play. Your answer should look like this. In this question, I'm being asked to use ruler and compasses to bisect the angle ABC. We all know that dissect means to cut something up. Bisect means to cut something exactly into 2 equal pieces. So I start by getting my pair of compasses and putting them on the corner of the angle. Here. I now open them out a little bit. The amount you open them doesn't actually matter, as long as you now don't change it throughout the rest of your drawing. Make a mark here and another one here. You now need to move the point of your compass to here. Move your pencil so that it's in between A and C and draw an arc. Now repeat this with the point of the compass at this point here. We now have a curvy cross. If we join this curvy cross to the point of the angle with a ruler, then we have bisected the angle. What this means is if we know the size of the angle is, let's say, 50 degrees, this will be 25 degrees, and this will be 25 degrees as well. We've cut the angle exactly in half. Here's a question for you to try. To start this, you need to draw yourself any right-angled triangle. Then bisect all three of the angles using a ruler and compasses. Press pause and have a go. When you're ready, press play. Your answer should look something like this. You know you've done it right if all three of your lines meet somewhere in the middle of the triangle. If you want to check if your answer is really accurate, then you can use your compasses. Put the point of the compasses where the lines cross and put the pencil here like this. If you then draw a circle, you should find that it touches all three sides of the triangle. We call this an inscribed circle. How well this circle fits inside the triangle is a good measure of how accurate your drawing was. Locus looks like a really difficult word, but the locus of a point just means the path traced out by the point according to a certain rule. If we have more than one locus, we call it loci. There are four basic situations that you need to know. The locus of a point that moves so that it's an equal distance from another point, 2 points, 2 lines, and a line. Let's look at each of these in turn. For this one, if a point moves so that it's always an equal distance from this point, then it will go in a circle around the point. You can see that any point on the circle will always be the same distance away from the point in the middle, and that distance is the radius of the circle. A point that moves so that it's always an equal distance away from 2 points will travel in a line straight down the middle. Any point on this line is the same distance away from this point as it is from this point, and we can think of this as bisecting a line. A point that moves so that it's an equal distance away from 2 lines will move through the middle of the 2 lines like this. You can think of this as being the angle bisector. It's cutting this angle here into 2 equal pieces. Finally, for a point that moves so that it's always an equal distance from a line, we have a slightly more complicated drawing. The point would move above the line and below the line. At the end here, you need to use a pair of compasses to draw an arc, and the same the other side. Now, exam questions aren't always this straightforward, and you need to learn to recognise which one of these situations to use. What we're going to do now is look at some practice questions that aren't quite exam standard, but will help you learn how to do it. Here's your first question. To do this, you'll need to draw a 12 by 7 grid on some squared paper, and then mark the point A here. It's 4 squares along and 2 squares down. Then show by shading the area in the rectangle which is more than 4 centimetres from the point A. Press pause and have a go. When you're ready, press play. I hope you realised that because this one is describing the distance from a point, you needed to start by drawing a circle with a radius of 4 centimetres around the point A. You then need to shade in the area which is more than 4 centimetres from A, and of course this will be all of the points outside the circle. So your shading should look something like this. Now try this question. You'll need a 12 by 7 grid again. Press pause and have a go. When you're ready, press play. Because we want to shade the area which is closer to BC, which is this line here, than to AD, which is this line here, we need to start by drawing the line that's exactly in the middle of them. Then, because we want to be closer to BC, we need to shade this side of the line. Here's another one for you. This time you want to shade the area which is closer to AB, that's this line along the top, than it is to AD, that's this line along the side. Please don't draw this line here. This will not help you and it's not going to give you the right answer. Instead, focus on these two lines and think about which of the 4 situations this relates to. Press pause and have a go. When you're ready, press play. Hopefully you realised that focusing on these 2 lines tells you that you need to bisect the angle here. So we've drawn a line very carefully at exactly 45 degrees. Now we want to shade the area closer to AB, that's this line remember, than AD. So we shade in this part here. Here's another one for you to try. This time you'll need a 12 by 7 grid with point A here, 4 centimetres from the end, and point B here, 6 centimetres from the end. In this question, you're focusing on 2 points, A and B. Remember to think about which of the situations at the start of this clip that this will relate to. Press pause and have a go. When you're ready, press play. Here's the answer. To achieve this, what I actually did was bisect the line that goes from A to B. Now here's your first exam style question. You'll notice that in an exam they give you the questions on plain paper, not on squared paper. You need to draw 2 points. The 2 points need to be exactly 8 centimetres apart. Once you've drawn your 2 points, make sure you read the question carefully. We're not finding the distance from 2 points. We're finding a distance from one point and a different distance from the other point. Press pause and have a go. When you're ready, press play. Your answer should look something like this. You needed to draw a circle around Acton with a radius of 4 centimetres. You might have drawn the whole circle, I've just drawn part of it. You needed to do the same thing around Burton, but with a radius of 5 centimetres. The important bit is where they overlap. This is the part that you needed to shade. Here's another exam-style question for you to try. You need to draw yourself a rectangle which is 12 centimetres across and 7 centimetres up. There is an oak tree in this corner here. Read the question through carefully and have a go. When you're ready for the answer, press play. Because I want the elm tree at least 4 metres from the oak tree, that's a distance from a single point. So I need to draw part of the circle with a radius of 4 centimetres here. All that's left to do now is shade in the region outside the circle. Here's your final exam-style question. This one's a really difficult one. You need to start by drawing a rectangle which is 10 centimetres across and 7 centimetres tall. Once you've done this, take this part 1 line at a time. You need to draw 3 things and then shade the right region. Press pause and have a go. When you're ready, press play. In the first part, we want to show the points that are at least 5 metres from the point C. That's a distance from a single point, so we know that it's going to be a circle. So we want a circle with a radius of 5 centimetres from the point C. Here, I've just drawn the part of the circle that's actually inside the rectangle. I know that my answer is going to be outside this circle somewhere. For the next part, we want to be nearer to AB than to AD. So we want to bisect the angle formed by these two lines. We get this line here. You can draw this line using a protractor, making sure that this angle is 45 degrees and this angle is 45 degrees. Or you can bisect the angle using compasses and a ruler. We want to be nearer AB than AD, so now we know we're in this region here. The last of the 3 things we need to draw is a line that's 3 centimetres from DC. You can measure 3 centimetres here and here with your ruler and then draw the line straight across. Because it says we want to plant the tree less than 3 metres from DC, we know we want to be below this line. So remember, we want to be outside the circle, this side of the diagonal line, but below this line. So now we need to shade in the correct region. And that is this part here. In this question, you will get 1 mark for drawing this arc, 1 mark for this line, 1 mark for this line, and 1 mark for shading the correct region. I'm being asked to use a ruler and compasses to draw a triangle. I'm told the lengths of the 3 sides are 10 centimetres, 8 centimetres, and 6 centimetres. I'm given the first side here. Before I begin, I'm just going to do a little sketch so that I know what I'm looking for as my end product. So the first side AB I know is 10. Then I've got AC, which has a length 8, and BC, which has a length 6. So C is going to be somewhere up here. Because AC is longer than BC, it's going to be somewhere like that. And we'll have 8 and 6, and that will be C. So my finished triangle is going to look something like this, and I just need to draw it accurately now. So now I need my ruler and compasses. Remember, I've already got the side AB drawn for me, so I'm going to start with AC, which is 8 centimetres long. So I open my compasses out to 8 centimetres. Because I'm drawing AC, I put the point of the compass on A now. Now I need to draw an arc with my compasses. Like this. The other side, BC, is 6 centimetres long, so I need to do the same thing but with my compass open at 6 centimetres. Because this time I'm doing BC, the point of the compass has to go on B this time. And again I draw an arc. Now where the 2 arcs cross is going to be the point C, and it's 8 centimetres away from A and 6 centimetres away from B. So I just need to join it up to make the triangle. So I've used a ruler to draw in the 2 lines. This is now my completed triangle. Leave in the construction lines as part of your working. They'll help you get the full marks for the question. Here's one of those for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Finally, if you want to see if your answer is correct, you can measure this angle here. It should be as close to 51 degrees as possible. I'm being asked to enlarge shape A by scale factor 2. What this means is that the length of each side will double. I can put my enlargement anywhere I like on the grid. So, the base here is currently 3 squares long. it will be 6 squares long on my new drawing. The side here is 3 squares. That will become 6 squares on the new drawing. This side is 2 squares. On the new version, it will be 4 squares. To finish off, I always get the last side for free, just by joining up these two. This is my finished enlargement with scale factor 2. In the second part, I'm asked to enlarge shape A by scale factor 1/2. Now, although it says enlarge, this is actually going to be smaller, because all of the sides are going to be half the length. So if I start with this side this time, it's 2 squares up here, so on my new picture, it will just be 1 square up. This is 3 squares across, so on my half-size one, it will be 1.5 squares across. This is 3 squares up, that will be 1.5 squares up. And again, I get the last side for free just by joining these together. This is my finished enlargement with scale factor 1/2. I could have drawn it anywhere that I wanted to on the squared paper. Here are 2 for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. Remember, your drawings just have to be the right size. They can be in any position you like on your piece of squared paper. This time, I'm being asked to enlarge the triangle by scale factor 2, but I'm given a cross to use as the centre of enlargement. This makes the question a little bit different. Our finished answer has not only got to be the right size, but it also has to be in the right position. I start this by drawing one guideline from the centre of enlargement through one of the corners. I'm going to choose this one. Like this. Now I need to count how I get from the centre to this corner. It's across 3 and up 2. Looking at my scale factor, I can see I've got a scale factor of 2, so I need to do this move twice. So across 3, up 2, across 3, up 2. This is the position of this corner on my larger shape. From this corner, it's 3 down, so on my enlargement, it will be 6 down. Then we've got 2 across, so on the enlarged version, we'll do 4 across. In the same way as before, we get the last side for free by joining these 2 points. This is my finished answer, and I'll get full marks for this, because it's the right size and it's in the right place. Here's one of those for you to try. You'll need to copy the shape and the position of the centre of enlargement very carefully onto some squared paper before you begin. Notice that this time your scale factor is 3. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. This time you'll need to draw the axes and the shape very carefully onto some squared paper. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. Here's another one for you to try. Again, you'll need to copy the axes and the shape carefully onto some squared paper before you start. Press pause and have a go. When you're ready, press play. So for this question, you should have started in your usual way with a guideline, which looks like this. To get to this corner from the centre of enlargement, it's across 6 and up 6. Now the scale factor is 1.5, so I need to do across 6 up 6 1.5 times. So that's across 6 up 6, and then across 3 up 3. This is the new corner. Now, on the original shape, this side is 4 squares long. If I multiply that by 1.5, that's 6 squares long. This side is 6 squares long. If I multiply that by 1.5, I get 9. In the usual way, we get the last side for free. This is what your finished enlargement should look like. This time I'm being asked to describe the single transformation that maps triangle A onto triangle B. Looking at it, I can immediately see that B is a different size to A, so this must be an enlargement. Now I need to find the scale factor. On A, this side is 3 squares long. On B, it's 6 squares long, so the scale factor must be 2. The last thing I need to find is the centre of enlargement. I do this by joining a corner to a like corner on the other shape and then carrying the line on. I need to do this for more than one corner, so I'm doing it for this one, and I'm going to use this one as well. The centre of enlargement is where the two lines cross, at this point here, which is 16, 7. To get all the marks for this question, you need all of these pieces of information. Here's one of those for you to try. You'll need to copy the axes and the shapes very carefully onto some squared paper. Press pause and have a go. When you're ready, press play. Here's the answer. Here's your final challenging exam-style question. Press pause and have a go. When you're ready, press play. Here's the answer. The area of triangle PQR is 1.5 centimetres squared. We want to achieve two things in this clip. We want to revise the parts of a circle we already know, and then learn about tangents, arcs, sectors, and segments. So this is what we already know. Take a few moments to refresh your memory on this. Now we're moving on to the new parts of the circle that we need to know. Let's start off by looking at tangents. This is not a tangent. Nor is this. Nor is this. But this is a tangent. A tangent is a line which touches a circle in exactly one place. An arc is a portion of the circumference of a circle. If I'm asked to look at arc AB, then I could either be looking at this part here or this part here. By convention, whenever it says arc AB, we take the shorter one in between the A and the B. So this is arc AB. If a question wants me to look at the larger part of the circumference, then it will ask me to look at the major arc AB. So we have two arcs, the minor arc and the major arc. Remember, if the question doesn't specify, then it will be the minor arc that you're looking for. A sector can be thought of as a slice of pizza. So sector AOB would be this slice of pizza here. Again, we have a minor sector and a major sector. If the question doesn't specify, then it will be talking about the minor sector. If it wants you to look at the major sector, then it will actually say that in the question. Now, when we draw a chord on a circle, it divides that circle into two segments. A minor segment and the larger major segment. Again, the same thing applies. If the question doesn't specify, then it'll be talking about the minor segment. Here's a summary of everything we've just learnt about circles. Here are some questions for you to try. The first thing you need to do is sketch the circle and the points A, B, C, D and O. Press pause and have a go. When you're ready, press play. Here are the answers. In this question, I've got a right-angled triangle and I'm given 2 of the sides. I'm being asked to find the third side. This tells me that this must be Pythagoras. So if I'm looking for the longest side, then I need to square, square, add and square root. I'm going to go through this in a moment. If I'm looking for a shorter side, I need to square, square, subtract and square root. Notice here it says shorter, not shortest. This applies to either of the 2 sides which aren't the longest one. Again, I'm going to go through this in a moment. So in this particular one, I'm looking for the longest side. You can always tell the longest side because it will be opposite the right angle. So I'm going to use this. I get my side, which is 9, and I square it. That's 81. I get the other side, 6, and I square that. That's 36. Now I add them. 81 add 36 gives me 117. Now I need to find the square root of 117. I can do this using a calculator. I'm rounding it to 1 decimal place and I get 10.8. So this side here is 10.8 centimetres long. So to summarise, if I'm looking for the longest side, I square it, add it, and then square root it. Now in this question, I can see that I'm looking for one of the 2 shorter sides. So I'm going to use this. This time, when I start with the first square, it's important to make sure I use the biggest side first. So I've got 8.5 squared. This gives me 72.25. The other side is 6.8. Squaring this gives me 46.24. Because I'm looking for a shorter side, I want to subtract. So subtracting these 2 gives me 26.01. Now I need the square root of this, and I get 5.1. So this side here is 5.1 centimetres long. So to summarise, when I'm looking for a shorter side, I square it. Remember to start with the longest side of the ones you've got. Then square it, subtract it, and then square root it. Here are 2 for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. The only way to get good at something is to practice, so here are 5 more questions for you. Press pause and have a go at them. When you're ready for the answers, press play. Here are the answers. Sometimes on the exam, you might be presented with a Pythagoras question in disguise. Look at this one for example. It doesn't ask you to find the length of the missing side. It's asking you to calculate the area of the triangle. However, the area of a triangle is the base times the height and then divided by 2. We need to know how long this is to be able to get the area, and we can find this length using Pythagoras. Press pause and have a go at this. When you're ready for the answer, press play. So I'm hoping that you realised that the missing side was one of the 2 shorter sides of the triangle. So you should have squared it, subtracted, and then square rooted. This gives you the side here, which is 24 centimetres long. Now that you've got that, you can use the formula for the area of a triangle and you end up with an answer of 84 centimetres squared. Now this is the hardest Pythagoras question in the world, so I'm going to give you some hints to help you with this. If you'd rather try it yourself without the hints, press pause and have a go now. In this question, we're looking for AC, which is this red line here. We could use Pythagoras to find this if we knew this side here. However, we don't know this side, so the first thing we've got to do is work it out. So to find this, I can draw the same length here and create a right-angled triangle. Remember, whenever we've got a right-angled triangle, we can use Pythagoras. I know how long this is because this whole thing is 9 and this part is 3. Now I can use Pythagoras to find this and then use this down here to find the length AC. Now press pause and try it. When you're ready for the answer, press play. So you should have used Pythagoras on this right-angled triangle here to calculate that x is 8 centimetres long. Remember, that tells us that BC is also 8 centimetres long. We're looking for AC, so now we need to use Pythagoras on this right-angled triangle here. This is the longest side of the triangle, so we use this now to calculate that the length of AC is 12.0 centimetres to 3 significant figures. And that's definitely the hardest Pythagoras question in the world. In any right-angled triangle, the side opposite the right angle is the longest one, and we call it the hypotenuse. If we draw a square on each side of the triangle, like this, then the area of this square, which is a squared, added to the area of this square, which is b squared, will always add up to the area of the biggest square, which is the one on the hypotenuse, c squared. This is Pythagoras' theorem, and we can use this formula to find missing sides in right-angled triangles. For instance, in this right-angled triangle here, I know 2 sides, and I want to find the third one. So I can use Pythagoras' theorem, a squared plus b squared equals c squared. Now the side I'm looking for is opposite the right angle. That makes it the hypotenuse, so it's the longest side, so this is C. The other 2 sides are A and B, and it doesn't actually matter which way round you put them. I'm going to call this one A and this one B. So A squared is 9 squared, plus B squared is 6 squared, equals C squared, which is X squared. Now 9 squared is 81, and 6 squared is 36, and this equals x squared. 81 plus 36 is 117, and this is x squared. So to find x, I need the square root of 117. I can do this using a calculator, and I get 10.8 to 1 decimal place. So this tells me that the length of x is 10.8 centimetres. Again, for this one, it's a right-angled triangle, and I'm looking for a missing side. So I have a squared plus b squared equals c squared. This time, this is the hypotenuse, so this is c, and these 2 here are a and b. So a squared is 4.9 squared, b squared is x squared, and c squared is 6.8 squared. So I use my calculator to work out 4.9 squared, and that's 24.01. I've still got the plus x squared, and I use the calculator for this part too, and that's 46.24. Now I need to rearrange this to get the x squared by itself. So I have x squared equals 46.24 minus 24.01. So x squared equals 22.23. Now to get x, I need to square root this using the calculator. And I get 4.7 to 1 decimal place. So the length of the side x is 4.7 centimetres. Here are two for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Notice that on the first one, when I got to this step, I just put this straight into the calculator and got this. I could then square root it. In a similar way, on the second one, from this stage, I rearranged it and then put this straight into the calculator to get this, which I could then square root. The only way to get really good at something is to practice. So here are 5 more questions for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Sometimes on the exam, you might be presented with a Pythagoras question in disguise. Look at this one for example. It doesn't ask you to find the length of the missing side. It's asking you to calculate the area of the triangle. However, the area of a triangle is the base times the height and then divided by 2. We need to know how long this is to be able to get the area, and we can find this length using Pythagoras. Press pause and have a go at this. When you're ready for the answer, press play. Here's the answer. Now this is the hardest Pythagoras question in the world, so I'm going to give you some hints to help you with this. If you'd rather try it yourself without the hints, press pause and have a go now. In this question, we're looking for AC, which is this red line here. We could use Pythagoras to find this if we knew this side here. However, we don't know this side, so the first thing we've got to do is work it out. So to find this, I can draw the same length here and create a right-angled triangle. Remember, whenever we've got a right-angled triangle, we can use Pythagoras. I know how long this is because this whole thing is 9 and this part is 3. Now I can use Pythagoras to find this and then use this down here to find the length AC. Now press pause and try it. When you're ready for the answer, press play. Here's the working and the answer for the first step, which is finding this length here, which in turn is this length here. And now that we have this, we're going to use Pythagoras on this right-angled triangle to find the red line. And we get this. So the final answer is 12.0 centimetres to 3 significant figures. And this is definitely the hardest Pythagoras question in the world. In this question, I want to calculate the shortest distance between the 2 points, P and Q. So the first thing I'm going to do is plot these 2 points onto the set of axes here. So P is -2, 1, and Q is 2, -1. Now the shortest distance between these 2 points will be the straight line that joins them together. We want to find the length of this line. In the question, it says that I've got to calculate the distance. This is telling me that I'm not allowed to get my ruler out and measure it. This question is actually a Pythagoras question in disguise. If I draw these 2 lines in here, I can see that I've got a right-angled triangle and I'm trying to find the length of the hypotenuse. This side here is 2 squares long, and this one is 4 squares long. So using Pythagoras, I'm going to square the 4, and that's 16, square the 2, and that's 4. I'm going to add them together because I'm looking for the longest side, and that's 20. So the answer will be the square root of 20. So I use my calculator to find this, and the answer to 1 decimal place is 4.5. Obviously, your working out might look a little bit different to this, but your answer should still be the same. Here's one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Here's your final question. This time you haven't been given any axes, so you might want to draw these yourself. Press pause and have a go. When you're ready, press play. Here's the answer. Obviously, your graph might look a little bit different to mine, but you should still get 5.4 as your final answer. We already know that two triangles are congruent if they're identical in size and shape. There are 4 formal ways to prove that two triangles are congruent, and you need to make sure that you know all of these. The first way is to show that all 3 sides of one triangle are the same as all 3 sides of another triangle. If we can prove this, then the triangles are congruent, and we can write down SSS, which stands for side, side, side. The second way that we can prove that two triangles are congruent is to prove that 2 sides and the included angle are the same in our 2 triangles. If we can do this, then we can write down SAS, side, angle, side. The third way is to prove that 2 angles and the included side are the same in our 2 triangles. And if we have this, we can write ASA, angle, side, angle. The last one is a little bit different, and it only works if your triangles are right-angled. If you're given 2 right-angled triangles, if you can prove that the hypotenuses are the same as each other, and any one of the other 2 sides, then you can write down RHS, right angle, hypotenuse, side. These are the 4 conditions for congruency. You need to know these off by heart. In the next part of the clip, I'm going to show you how to use them. So here's a question. We're told that PQR is an isosceles triangle in which PR, that's this here, is equal to PQ. We're told that A and B are points, so that angle AQR, that's this angle here, is equal to angle BRQ, that's this angle here. I've got to prove that triangles QAR and RBQ are congruent. So the first thing I like to do is highlight the 2 triangles I'm looking for. So QAR is here and RBQ is here. Then I like to draw these out separate to the original diagram. You'll see why I'm doing this as we go along. So I've got AQR, just a sketch, it doesn't have to be tidy, and BQR. So now I want to prove that these 2 triangles are congruent using the information that I'm given in the question. When I write my conditions for congruency, I'm going to write them as bullet points. Don't waffle, leave the waffle for your English essays. This is maths and we're going to do it precisely. Straight away, I can see that this side here, QR, is common to both of the triangles. So that's going to be my first bullet point. QR is common. And I can mark that on my diagrams. This length is the same as this length. Here, I'm told that angle AQR, that's this one here, on my diagram it's this one, is equal to angle BRQ, this one, which is this one. So I can write this down as a bullet point. Angle AQR equals angle BRQ, and I know this because I'm given it in the question. Now let's have a look at what we've got so far. We've got a common side and an angle. If I look at my conditions for congruency, this one includes an angle and a side, and so does this one. So I think I'm going to use one of these two. So if I can find another side or another angle, then I know I've got two congruent triangles. I can't get any more information immediately from the diagram, so let's go back into the words. I'm told here that PQR is an isosceles triangle. Now they can't have given me this piece of information for no reason, so let's look what it tells us. Well, it tells us PR is equal to PQ, that's these two sides here. But we also know that in an isosceles triangle, this angle here will be the same as this angle here. Now this angle is BQR, which is in this triangle here. And this angle is ARQ, which is in this triangle here. So I now know that these two angles are the same, and I need to write my bullet point for this. So angle ARQ is equal to angle BQR, and that's because they are the base angles of an isosceles triangle. So I've now got two angles and the included side in each triangle. So that tells me I've got this condition for congruency. So to finish the question, I must write a concluding statement. I've proved that triangles QAR and RBQ are congruent, and I've used the ASA conditions for congruency to prove this. Make sure when you do a question that you write your concluding statement and that your work is in bullet point form so that you're not waffling. Here's a question for you to try now. One thing to notice is that you've got a right angle marked here and here. So that should give you a clue as to which of the four conditions for congruency you're going to be using in this question. Press pause and have a go. When you're ready, press play. Your answer should look something like this. I hope you found these three bullet points. They can be in any order. The big one is this one here. You needed to realise that BD is equal to AC because these are diameters of the same circle. AD is common to both, and we have the right angles as well. Don't forget to write your concluding statement and to say which condition for congruency you've used. Here's another question for you to try. Remember when you're doing this question that the proper name for a Z angle is an alternate angle. Press pause and have a go. When you're ready, press play. Here's the answer. Now here's a particularly demanding question for you to try. The good news is you don't get many like this, but if you can do it, you're a real star. To help you a little bit, these are the two triangles that you're going to try and prove are congruent to each other. Press pause and have a go. When you're ready, press play. Here's the answer. The hardest bit of this answer is to get that angle DAG is equal to angle BAE, and the reason why. If we look at the diagram here, we can see that angle DAG is this right angle because it's a corner of a square, plus this angle here. And we can see that angle BAE is this right angle, the corner of a square, plus that same angle. I write it out like this. They're both 90 degrees plus DAE. In this clip, we're going to be looking at sectors of a circle. In this first question, I'm asked to find the area of the sector here. Now, I already know the formula for the area of a circle. That's pi r squared. If the sector was just 1 degree of the circle, then I would multiply this by 1 over 360, because I would have 1/360th of the circle. But my sector isn't just 1 degree, it's 220 degrees. So I'm going to have 220 over 360 times pi r squared, and this will give me the area of the sector. So I've got 220 over 360 multiplied by pi multiplied by r squared, which is 19 squared. At this point, I can now use a calculator to work out the answer. I just type in 220 divided by 360 times the pi button times 19 squared. And I get the answer 693.070246. The question doesn't tell me how to round my answer, so I could round it to 3 significant figures, or to 1 decimal place would seem reasonable. I'm going to do it to 1 decimal place, so it's 693.1. Finally, it's an area, so the units are going to be centimetres squared. This is the area of this sector of a circle. Here's one for you to try. Remember, you can use a calculator and round your answer to 1 decimal place. Press pause and have a go. When you're ready, press play. Here's the answer. Now this question looks very similar, but this time I'm being asked to find the perimeter of the sector of the circle. Now the perimeter, of course, is the distance all the way around the outside of the shape. So that's the curved part here, and this straight line and this straight line, which of course are both radiuses of the circle. So I'm going to work out the curved part of the perimeter first. Now I know that the circumference of a circle is 2 pi r. So the curved part of the perimeter must be 220 over 360 times 2 pi r. So I have 220 over 360 times 2 times pi times the radius, which is 19. And again, I can use a calculator to work this out using the pi button. Rounded to 1 decimal place, I get 73.0. Now remember, this isn't the whole perimeter yet. This is just the part that's highlighted in yellow on the diagram. I now need the green part. We know that this is 19. This must be 19 as well. So I can get this and add on the 2 19s. So I've got 73.0 plus 19 plus 19. So I get 111.0. Finally, this is a perimeter, so we're measuring a distance, so the units are centimetres. And this is my final answer to 1 decimal place. Here's one for you to try now. Press pause and have a go. When you're ready, press play. Here's the answer. Because in this question I was asked to show something, I need to write a concluding statement, and I've written it here in 2 ways, with a sentence and with mathematical notation. You just need one of these. Here's a more difficult question for you to try. Any information given in the question here, you're probably going to have to use. That's the only clue I'm going to give you. Press pause and have a go. When you're ready, press play. Here's the answer. The clue was to work out that because triangle OAB is equilateral, we've actually got a sector of a circle here with a 60-degree angle at the top. Now in this slightly harder question, I'm given the arc length of the sector here, and I'm asked to calculate the value of the angle x. I know that the formula for the arc length is the angle over 360 multiplied by 2 pi r. Now I know that the arc length is 10.5. I don't know what x is yet, so I'm going to leave that in. But I've got 2 times pi times r, the radius, which is 8. Now from this line here, I want to find a value for x. There are many different ways of doing this, and I'm just going to show you one of them. What I'm going to do is multiply out this part here first of all. So I've still got 10.5 equals x over 360 multiplied by 50.27. I've got this number by typing this into a calculator and rounding to 2 decimal places. The reason I've rounded to 2 decimal places is because I'm given 1 decimal place in the question, so I always work with 1 extra decimal place until I get to my final answer. Now I can divide both sides by 50.27, so I get 10.5 over 50.27 equals x over 360. And now I can multiply both sides by 360, so I get 10.5 over 50.27 times 360, and that will give me a value for x. I'm going to use my calculator again to do this. I get x equals 75.2, and this time I've rounded to 1 decimal place because this is my final answer. Finally, it was the size of this angle, so the units are degrees. Here's a question for you to try. Be careful, this time you're given the area of the major sector. That means the area of this part here. Press pause and have a go. When you're ready, press play. Here's the answer. Whenever you see a question like this, with a right-angled triangle and an angle, you're going to be using trigonometry. To be able to do trigonometry, you need to use these 3 formula triangles. You need to learn these off by heart because they won't be given to you on the exam. Now, before I start the question, I need to make sure that I read it. It's asking me to find the length of side AB. That's this side here, so I'm going to call that x. Now I'm ready to start the question, and there are 4 very clear steps that I need to follow. Step 1 is to label the sides. In trigonometry, each of the sides of this triangle has a special name. We start by finding the angle. This side here, which is opposite the angle, is called the opposite. We can just put O. This side here, the longest side, is the hypotenuse. We just call that H. And then the last side here is actually adjacent. It's adjacent to the angle. We just call it A. You don't actually need to remember what adjacent means because it's always going to be the last side you find. So remember, the last one is always A. Now it's absolutely crucial that you get these 3 labels right. If you get this wrong, it doesn't matter how good at maths you are, everything else will fall apart. So I'm going to give you some practice on labeling the 3 sides of a triangle. So here are some triangles for you to label. You'll need to make a sketch of them, labeling the right angle and the angle. Then label the sides O, A and H. Press pause and have a go. When you're ready, press play. Here are the answers. Now the second step is to cross out the unwanted side. This is a nice quick step. We want this side because it's going to help us because we've got a value for it. We want this side because this is the one we're looking for. This one, though, hasn't really got anything to do with the question, so we cross it out. For step 3, we need to choose the correct formula triangle from these 3 up here. If we look at our question, we've got A and H. These will only appear together in one of the 3 formula triangles. It's this middle one here. Now in the final step, we need to use our formula triangle. So I'm going to write it out like this. Now I need to use this triangle to make a formula. The side I'm looking for is this one here, x, and I can see that that's the A. So I'm looking for the A. So I cover it up, and the 2 that are left are next to each other. That tells me it's going to be a times. So I've got C times H. Now I need to write down what these 3 things really are in the triangle. So A, look, is x. C stands for cos, and it's cos 53. And H is 8. Now you're going to use a calculator to work this out. When you type this part into your calculator, it might open a bracket here. If it does, you need to make sure that you close it again. So typing this in and rounding to 3 significant figures gives 4.81. Remember, what we've just found is the length of this side here. So the units for this will be centimetres because it's a length. So we have 4 clear steps. Label the sides, cross out the unwanted side, choose the correct formula triangle, and then use it. Just out of interest, if you do this exactly as it says here and type this into your calculator exactly like this, but don't get the answer 4.81, that's telling you that your calculator is in the wrong mode and you'll need to change it to degrees mode. So we're going to do this question together now, step by step. The first thing you'll need to do is make a sketch of it. Then I'd like you to do step 1, label the sides. Press pause and have a go. When you're ready, press play. You should have this. I hope you remembered that because we're looking for the side AC, you need to label that X. Now try step 2, cross out the unwanted side. Remember, this is a really fast step. Press pause and have a go. When you're ready, press play. So we're looking for X, so we need to keep H. We know the 12, so we need to keep O, so we cross out the A. Now I'd like you to try step 3. Choose and write down the correct formula triangle. Press pause and have a go. When you're ready, press play. You should have realised that because we've got O and H, we need this one here, and you should have written it down. For the last step, you need to use your triangle to create a formula and then find the length of side AC using that formula. Press pause and have a go. When you're ready, press play. So we're looking for X, which is H. So we write down H equals and then cover it up in the formula triangle. Now we're left with O on top of S. That tells us that it's O divided by S. Now we need to replace these with what we know from the triangle. So H is actually X, O is 12, and S stands for sine, and it's the sine of the angle, which is 31. Remember, if your calculator opens a bracket here, you need to close it. We now type this into our calculator. Rounding to 3 significant figures, we get 23.3. This is the length of this side here, so the units are centimetres. Here's one for you to try on your own now. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. We're now halfway through trigonometry. You can find any side when you're given an angle and a side. Now we need to learn how to find angles, and we do this when we're given 2 sides. It's very, very similar to the method we've been using. So I want to find angle ABC. So the first thing is to find which angle this is. ABC is this one here, so I label it with my X. Now I follow my 4 steps. I start by labelling the sides. So opposite the angle is O, the longest side is H, and the other one is A. I then cross out the unwanted side. So I've got this one here, I've got this one here, but I don't have anything on this one, so I can cross this one out. Then I choose the correct formula triangle. I've got O and H, so it's going to be this triangle here, and I write it out. Now I use the formula triangle. I'm looking for X. Now remember, that's the angle, so that's sine X, so that's S. I cross it out and I can see that it's O over H. Now S is sine and it's sine x. O is 5 and H is 8. So up until this point, everything has been the same. Now we can do 5 divided by 8 in our calculator, and this will give us sine x, and that's 0.625. Now you might be tempted to stop here, but think about what you've done. We're looking for this angle here, and at the moment we have 0.625. There's no way that this angle can be less than 1 degree. Also, we've still got the sine bit here. So we need to get rid of this, and this is the big difference when you're finding an angle. To find the value of x, you need to press the shift button or the second function button, depending on which one you've got on your calculator, sin, and then equals. So make sure you've got this on your calculator screen to start off with, then press shift or second function, sin, equals, and you should get the answer 38.7 rounded to 3 significant figures. This is the size of the angle here, so the units this time are degrees. So here's a question for you to try where you need to find an angle. Press pause and have a go. When you're ready, press play. Here's part of the working. Once you get to this stage here, you need to remember to press shift tan equals. You should get 57.7 to 3 significant figures, and this is degrees because it's the size of the angle here. Here's another one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Now, trigonometry is a topic that appears every year on the exam papers, and the only way to get good at it is to practice. So here are 5 questions for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. I hope you didn't let E fool you. You're given all 3 sides here, so you can actually cross out any one of them. That will then mean that you can use 3 different formulas, and whichever one you use will give you the right answer. In exams, they often like to give you a trigonometry question in some kind of context. Here's an example of that. The method is exactly the same, just take care over this one and you should be fine. Press pause and have a go. When you're ready, press play. Here's the final answer. You should have found this side here of the triangle using trigonometry, and that's 21.01. You needed to realise that the height of the building was this plus the height of the man. So that's 21.01 plus 1.7. This gives you the total height of the building, and that's 22.7 metres. Here's another trigonometry question in a context for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. The lovely thing about spheres is that they're only defined by one dimension, the radius. If you want to find the volume of a sphere, you use this formula, which involves the radius. If you want to find the surface area, you use this formula, which involves the radius. These 2 formulae will be given to you on the exam paper. Let me show you how to work out the volume and surface area of a sphere. For the volume, I need to use this formula. So I've got V equals 4/3 times pi times r, which is the radius, that's 5, cubed. Now, whenever you see a pi symbol like this, I'm going to be using the pi button on my calculator. If your calculator doesn't have a pi button, you can use the number 3.142, but you might get a slightly different answer. I now type this into my calculator. 4 divided by 3 times by pi using the pi button, times by 5 cubed. I get the answer 523.6 centimetres cubed. You'll notice that I've given my answer to 1 decimal place. That's because it doesn't specify how many decimal places to do in the question. A good rule when they don't specify is just to do 1 decimal place. For the surface area, I'm going to use this formula. So the surface area is 4 times pi times the radius, that's 5, remember, squared. Again, I'm going to use the pi button on the calculator. Typing this in gives me 314.2 centimetres squared. Again, notice that I've rounded to 1 decimal place. Here are some for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. In this question, I'm told to leave my answer in terms of pi. This type of question would be on the non-calculator paper. It looks more difficult, but actually it's not much harder. I want to find the volume, so I'm going to use this formula. So the volume is 4/3 times pi times the radius, which is 6, cubed. Now remember, I can't use a calculator to help me with this part, so the first thing I'm going to do is the 6 cubed. That is 216. So I've got 4/3 times pi times 216. Now I want to rearrange this to put the pi at the end. So I've got 4/3 times 216 times pi. Now there's only one thing left to do, and that's to work out what 4/3 of 216 is. The easiest way to do this is to divide 216 by 3 and then multiply by 4. I'm going to do this as a piece of side working. Doing this gives me 288, so the answer is 288 times by pi, which I can write as 288 pi. This is a volume, so the units are centimetres cubed. You can see that I've got pi in my answer, so I've done exactly what they've said and got my answer in terms of pi. Just out of interest, if you found this part a little difficult and wanted to make it a bit more straightforward for yourself, you could do this. Instead of working out what 6 cubed is, I could write it as 4/3 times pi times 6 times 6 times 6. Now I cancel the 3 here with one of the 6's to give me 2, and I can now work out the answer. So I have 4 times 2, which is 8, times 6, which is 48, times 6 again. You can do a bit of working to get this, but the answer is 288. I've still got the pi symbol, and remember the units are centimetres cubed. Here are some for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Here's another question for you to try. You're not leaving your answer in terms of pi this time, so you can use a calculator. Press pause and have a go. When you're ready, press play. You need to remember that a hemisphere is exactly half of a sphere. So to start with, I'm going to find the volume of the whole sphere. That's given by 4/3 times pi times the radius, which is 7, cubed. Now I type this into my calculator and I get 1,436.75504 centimetres cubed. Because this is a working out stage, I've written down the whole answer. On my calculator, I've left the answer on the screen ready for the next part. To find the volume of the hemisphere, that's going to be exactly half of this, so I'm just going to halve this number. Remember, I've left this on my calculator screen, so all I need to do is press divide by 2. I get 718.4 centimetre cubed. This time I've rounded it off to 1 decimal place because this is my final answer. Here's a harder question for you to try. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. To get this, you should have found the volume of the cuboid, the volume of the sphere, and then halved it to get the volume of the hemisphere, and then added the cuboid and the hemisphere together to get the final answer, which I've given to 1 decimal place. Here's another question for you to try. This time you'll notice that you're being asked for the total surface area of a hemisphere. That means you're going to need the curved surface area and the flat base. Leave your answer in terms of pi, so don't use a calculator for this one. Press pause and have a go. When you're ready, press play. Here's the answer. It's in terms of pi, and make sure that you've got centimetres squared, not centimetres cubed, because this is an area, not a volume. Here's another difficult question for you to try. You can use a calculator for this one. Press pause and have a go. When you're ready, press play. Here's the answer. A pyramid is any shape that goes up to a point at the top. The volume of a pyramid is given by 1/3 times the base area times the height of the pyramid. This formula will not be given to you on your exam paper, so you need to memorize it. Once we know this formula, it becomes fairly simple in most cases to find the volume of a pyramid. For example, this pyramid here has a rectangular base, so the base area is 6 times 5, which is 30. To find the volume of the pyramid then, I have 1/3 times the base area, which I've just worked out, that's 30, times the height, which is 8. Now, 1/3 times 30 is 10, so that's 10 times 8, and that's 80 centimetres cubed. Here's a question for you to try. Do this one without using a calculator. Press pause and have a go. When you're ready, press play. Here's the answer. Here's a more difficult question for you now. The key to this is to realise that the central part here is in the shape of a perfect cube, so all the measurements are 8. Once you know this, you can work out the heights of the 2 pyramids because it also tells you that the pyramids are identical to each other. You can use a calculator for this question. Press pause and have a go. When you're ready, press play. Here's the answer. Here's the world's most difficult pyramid question. You're asked to find the volume of the pyramid, and to do this, you need the height. Now, to find the height, you need to be good at Pythagoras, because you've got to find this length here, and then you can find the height here. You can use a calculator for this one. Press pause and have a go. When you're ready, press play. Here's the answer. We already know that the definition of a pyramid is any shape that goes up to a point at the top, and we know the formula for the volume of any pyramid. Now, a cone is just a pyramid with a circular base, so we can use this same formula. The base area is going to be the area of a circle, so this is given by the formula pi r squared. So the formula for the volume of the cone is 1/3 times pi r squared times the height. We write this as 1/3 pi r squared h. This formula is actually given to you on the exam paper. The other formula that you need for cones is this one here. We find the curved surface area by using pi times r times L. L is this measurement here. We call it the slant height of the cone. The curved surface area refers to the surface area around the cone here. In other words, any part that's curved and does not include the flat circular base. Again, this formula is given to you on the exam paper. So to find the volume of this cone, I use this formula. So V equals 1/3 times pi times r squared, that's 3 squared, times h, that's 4. I'm going to use a calculator to get the answer for this. I'm going to type in 1 divided by 3 times pi. I'm going to use the pi button, but if you don't have a pi button, you can use 3.142 times 3 squared times 4. My calculator gives me the answer 37.7 rounded to 3 significant figures. The units are centimetres cubed because this is a volume. For the curved surface area, I need to use this formula. So the curved surface area is given by pi times r, which is 3, times L, the slant height, which is 5. Again, I can type this into a calculator using the pi button for pi. I get the answer 47.1. Because this is a surface area, the units are centimetres squared. Finally, I want to find the total surface area. Now, the total surface area is the curved surface area plus the flat circular base. Remember, we already know the curved surface area. We've just worked that out in part B. So for the total surface area, we've got the answer from part B plus the circular base, which is given by pi times r squared. R is 3, so that's 3 squared. Again, I use a calculator for this, and I get the answer 75.4. It's an area, so the units are centimetres squared. Here are some for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. In this question, I'm being asked to find the volume, but to leave the answer in terms of pi. This type of question could be on the non-calculator paper. We approach it in the same way using the formula. So volume is 1/3 times pi times r squared, that's 6 squared, times the height, which is 5. I'm going to rearrange this slightly so that pi is at the end. So I've got 1/3 times 6 squared times 5 times pi. Now 6 squared is 36. And now I can find 1/3 of 36. That's 12. So I've got 12 times 5 times pi. Now 12 times 5 is 60, and the pi just goes on the end. This is the answer in terms of pi, and the units are centimetres cubed. Here's one of those for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Now this question looks very similar to the last one. I'm being asked to find the volume in terms of pi. If you look carefully at the diagram though, you'll notice that this time we've been given the slant height rather than the height. So the first thing we need to do is use Pythagoras' theorem to find the height of the cone. I'm going to draw a little triangle to help me with this. So this triangle here is this section of the cone. The base is 8 and the slant height is 17. I want to find the height. I know that the height squared will be 17 squared minus 8 squared using Pythagoras' theorem. I'm going to use a calculator for this and I get 225. I can square root this to find the height. That is 15. Now I know the height, I can use the formula for the volume. So the volume is 1/3 times pi times the radius squared, that's 8 squared, times the height, which is 15. This is a calculator question, but I need to leave it in terms of pi. So when I type this into the calculator, I'm just going to type 1/3 times 8 squared times 15, and I'm going to leave the pi out. I get 320, and I can put the pi back on the end. The units are centimetres cubed. Here's one of those for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. In this question, I'm given the volume of the cone and I want to work out the height. I start with the formula. So the volume of a cone is 1/3 times pi times r squared times h. Now I fill in values that I know. The volume is 324 pi. 1/3 is just 1/3, and pi is just pi. R squared is 9 squared. And h is what I'm looking for, so that stays as h. Now at this stage, don't be tempted to carry on working with the pi's here. Because I've got a pi appearing on both sides, I can divide by pi, which will eliminate it. So I get 324 equals 1/3 times 9 squared times h. So 324 equals 1/3 times 81 times h. Now 1/3 of 81 is 27, so I know that 324 is 27h. To find h, I can divide 324 by 27. I'm not using a calculator, so I'm going to do this as a bit of side working. 27 doesn't go into 3, but it does go into 32 once with a remainder of 5, and 27 goes into 54 twice. So, h is 12 centimetres. Here's one of those for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Now here's the world's hardest cone question. You need to think about this really carefully. Just have a go at it. Press pause and try. When you're ready, press play. Here's the answer. To get this, I started off by finding the volume of the sand here. This is in a cylindrical shape, so I actually use the volume of a cylinder with a radius of 3 and a height of 4. This is the volume of the sand. When we tip it upside down, we can see that the cone is completely filled and then there's a bit more. What I did was find the volume of the cone. Remember, we know that the height of the cone is 2 and the radius of the cone is 3. So the volume of the cone is this. I then took this away from the original volume of sand. That gives me this part here. Now again, this is just in the shape of a cylinder with a radius of 3 and an unknown height. I used that to find the height. Once I'd done this, I needed to add it on to 2 to get the height x, which is what I'm looking for. This is the final answer. If we have a cone and we take off a smaller cone, then what we're left with is called a frustum. In an exam, you might be asked to find the volume of a frustum. So here's a typical exam question. To find the volume of the frustum, I'm going to find the volume of the large cone and subtract the volume of the small cone. So I start with the volume of the large cone. The formula for the volume of a cone is up here. It's 1/3 times pi times the radius squared. Now the radius of the large cone is going to be 6. And then times that by the height, which is 15. I'm going to use a calculator to do this, and when you see the pi symbol, I'm going to be pressing the pi button. The answer I get is 565.4866776. I'm now going to work out the volume of the small cone in the same way. So we have 1/3 times pi times the radius squared. The radius of the small cone will be 4 times by the height, which is 10. Again, I'm using a calculator for this, and I get 167.5516082. To find the volume of the frustum, I get the volume of the large cone and subtract the volume of the small cone. I'm going to subtract these using a calculator and round my answer to 1 decimal place. I get 397.9, and the units are centimetres cubed because we found a volume. Here's one of those for you to try. Remember to give your answer to 1 decimal place. Press pause and have a go. When you're ready, press play. Here's the answer. This question looks very similar, but there's a slight complication which will become clear as I do the question. I'm going to start again with the volume of the large cone. So that's 1/3 times pi times the radius, which is 6, squared times the height, which is 18. Using a calculator, I get the answer 678.5840132. The next thing I want to do is find the volume of the small cone, but if you look at the diagram carefully, you'll see that we don't know this distance here, so we don't know the radius of the small cone. That means I've got to find it, and I'm going to do that using similar triangles. So, if I imagine that the large cone looks like this, we've got a base of 12 and a height of 18. The smaller cone is just the top part of this triangle. I don't know the base, but I do know that the height is 15. Now 18 divided by 15 is 1.2, so the scale factor here is 1.2. If I divide 12 by 1.2, I get 10, so I know that the base of the smaller cone here is 10 centimetres. Now I can find the volume. So I have 1/3 times pi times the radius, which is going to be 5, squared times the height, which is 15. Using a calculator, I get 392.6990817. Now to find the volume of the frustum, I subtract the volume of the small cone from the volume of the large cone. And that gives me 285.9 to 1 decimal place, and the units are centimetres cubed. Here's one of those for you to try now. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. For the exam, you need to know all of these values. You either need to memorise them or have a way to work them out without using a calculator, because they will appear on the non-calculator paper. I'm going to show you a method for working them out without using a calculator. For this method, you need to use your left hand or a sketch of a left hand like I've got here. You need to know that these values belong to each of these fingers. When you're starting to learn this method, you can actually write them on with a pen if you want to. You need to remember 3 things. Sine is on the left and cos is on the right. I'll explain this in more detail in a moment. We square root the fingers and divide by 2. This sounds really weird, but I'm going to show you exactly what I mean. So let's say we wanted to work out what cos 30 was. You put down the finger with the 30 on it. Now obviously on my sketch I can't put that down, so I'm just going to scribble it out. I want cos 30. Cos is on the right, so I count how many fingers are on the right. I can see I've got 1, 2, 3. Now it tells me to square root the fingers, so that's the square root of 3, and divide by 2. So the value of cos 30 is root 3 over 2. So we now know that cos 30 is root 3 over 2. Let's do sin 30 now. We want to put down the 30 finger. Remember on my diagram, I'm just scribbling that out. Sin is on the left. There's 1 finger on the left. Remember, we square root the fingers, so that's the square root of 1, and divide by 2. Now the square root of 1 is actually just 1. So this is actually a half. So we now know that sin 30 is a half. I'm going to do one more before I let you have a go. I'm going to do cos 90. So we put down or scribble out the 90 finger. Cos is on the right. There are no fingers on the right. So when I square root the fingers, that's the square root of 0, and divide by 2. The square root of 0 is 0, and 0 divided by 2 is still 0. So cos 90 is 0. Now can you try using this method to calculate sin 60 and cos 60? Press pause and have a go. When you're ready, press play. So your working out should look like this. And sin 60 is root 3 over 2, whilst cos 60 is a half. Now that you've got the hang of this method, calculate the remaining 5 values of sin and cos. Press pause and have a go. When you're ready, press play. Here are the answers, and you can check your working out down here. Now I can hear you saying, that's all well and good, but what about tan? Well, there's a slightly different method for tan. We divide the fingers on the left by the fingers on the right, and then square root. So, let me show you tan 30. We scribble out the 30 finger, or if you're using a real hand, of course, you can just put that down. The fingers on the left, we've got 1. For the fingers on the right, we've got 3. So we've got 1 divided by 3. We then square root this. Now this gives me root 1 over root 3. The square root of 1 is 1, so this is just 1 over root 3. In the same way, for tan 0, I scribble out the 0 finger, divide the fingers on the left, that's none, by the fingers on the right, that's 4, and then square root. Now this is the square root of 0 divided by the square root of 4. The square root of 0 is 0, square root of 4 is 2, but 0 divided by 2 is just 0. So tan 0 is actually 0. Now try and work out these two yourself. Press pause and have a go. When you're ready, press play. Here are the answers with the working out over here. If you're wondering why you don't have to know tan 90, try using this method to work it out, and you'll soon see why. Now picture the scene. It's exam day. Yesterday you fell off your bike, broke your arm, and your left hand is entirely in plaster. Is there anything you can do to rescue the situation? Well, yes, actually, there is. You can use a bit of maths to help you. You need to start by drawing an equilateral triangle. It's got sides of length 2. Drop a perpendicular down here, so we've now got a right angle. Because it was an equilateral triangle, we know that there's a 60-degree angle here, and we've cut this one up here in half, so this is 30 degrees. I'm going to just take this part of the triangle now and enlarge it a little. Now we know that the base here is 1 because it's half of this length of 2, and we can work out this using Pythagoras' theorem. So using Pythagoras, I know that this length x is now root 3. Now, using simple trigonometry, I can work out sin, cos and tan for 30 and 60. So, for example, if I want the sin of 60, that's the opposite over the hypotenuse, so that's root 3 over 2. If I want the cos of 30, that's the adjacent over the hypotenuse, so that's root 3 over 2. And if I want the tan of 60, that's the opposite over the adjacent, so that's root 3 over 1, which is just root 3. So this triangle will get all the values of sin, cos and tan for 30 and 60 for you. Now let's look at how we do 45. We need a slightly different triangle. We're going to draw a length of 1, a base of 1, so we have a right angle here, and a hypotenuse. This angle will be 45 degrees, and this angle will be 45 degrees. In the same way as before, I can use Pythagoras to work out the length of the hypotenuse. That's root 2. And again, using basic trigonometry, I can now find all the values of sin, cos and tan for 45 degrees. For example, sin 45 is opposite over hypotenuse. The opposite is 1 and the hypotenuse is root 2, so sin 45 is 1 over root 2. If you understand all of this, then it shouldn't be too difficult for you to memorize these values as well, and once you've got all of that, then everything is covered. Now, using any of the methods that I've just shown you, write down the exact values of all of these. Press pause and have a go. When you're ready, press play. Here are the answers. I want to describe the translation of shape A to shape B using a vector. The first thing I need to do is look how shape A has moved to get to shape B. To do this, I need to choose two corresponding points on the shapes. So I choose this point here on A and the same point on B. I always need to go across first. So I go across in this direction, 5 squares, and up in this direction, 3 squares. Now, because I've had to go to the left, then I need to write this as -5. And because here I've gone up, then this needs to be written as +3. I'll explain about this in a moment. Our final answer for V is a vector which looks like this, with our across number on the top, that's -5, and our up and down number on the bottom, that's +3. I can just write 3 here. Now let me just explain about the rules for vectors. Your vector will always have your left and right number on the top and your up and down number on the bottom. If you go in this direction to the right, that's a plus, and if you go to the left, that's a minus. If you go up, that's a plus, and if you go down, that's a minus. If you find it difficult to remember which ones are pluses and minuses, just think about a set of axes. The plus numbers are over here, to the right, and the minus numbers are over here, to the left. In the same way, the plus numbers go up, and the minus numbers go down. Also, when plotting coordinates, we always start with the x-axis followed by the y-axis. So that's why the top number is always across and the bottom number is always up or down. So to summarise, for the vector here, I started by going 5 to the left, so that's -5 following these rules, and 3 up, so that's a 3 following these rules. Here's one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Now in this question, I'm given two column vectors. The column vector f is 3 minus 5. This means that I'm moving across 3 and then down 5. So my net result is the vector f, which looks like this. It's defined by two things. It has a length and it has a direction. In exactly the same way, the vector g would look like this. Now I want to work out a column vector to represent 3f. This means that I'm going to do vector f 3 times, one after the other. So as a picture, my vector would look like this. Using this, I can see that to get my final answer for my column vector, I just need to multiply all of the numbers here by 3. So to get my answer for 3f, I just do 3 times 3, which is 9, and 3 times -5, which is -15. Now for the vector f plus g, that tells me I'm going to do vector f, and then on the end of that, I'm going to do vector g. I get this picture here. The column vector I'm actually looking for is going to be the vector that represents this here, which is the resultant vector. So to get my answer, I get the column vector for f, which is 3 minus 5, and I simply add on the column vector for g, which is 2, 4. So I've got 3 plus 2, that's 5, and I've got -5 plus 4, that's -1. This is the answer. Now C is interesting. It's asking me to do minus f. So that's going to be minus the column vector for f, which is 3 minus 5. So I've got -3, and I've got -5, which is 5. If we draw a diagram of this one, we're going left 3, and then up 5. So the resultant vector looks like this. Compare this to this one, and you'll see we have exactly the same length, but we've changed direction from going down this way to going up this way. This tells us that whenever you take the negative of a vector, it switches the direction of it. And of course, if you want to switch the direction of a vector, then you take the negative. Finally, for this one, I've got 4f, so 4 times 3 is 12, and 4 times -5 is -20, minus 3g. 3 times 2 is 6, and 3 times 4 is 12. Now I've got 12 minus 6, so that's 6, and I've got -20 minus another 12, so that's -32. This is the answer for this one here. Now here are some for you to try. You don't need to do any diagrams, I just did those to show you how things work. We're looking for your answers as column vectors. Press pause and have a go. When you're ready, press play. Here are the answers. We know that vectors always have a length and a direction, and we're asked to write each of the vectors C, D and E, they're here on the diagram, in terms of A and B, they're these two. So if we look at vector C, I can see that I want to go from this point here to this point here. I want to get there only using A and B. So if I use A first, I go across one like that, that's A. And then if I put B on the end of it, I go up like that, and that's B. So I can see that the vector C is what I get if I do A plus B. Now I want to do D in the same way. Now looking at D and comparing it to A, I can see that it's just 3 times the length of A. So I've got an A here, an A here, and an A here. So the vector D is actually just 3A. Finally, for E, remember you want to start here and end up here, only using A and B. So if I do A first, I go across to here, and then B looks like it will fit, but B's going the wrong way because I want to go across then down. How can I switch this so that it's going the other way? Well, I can make it minus B. So the vector E is A minus B. Here are some of those for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. I'm being asked to enlarge this triangle by scale factor -2 with the centre of enlargement 1, 1. The first thing I'm going to do is plot the centre of enlargement onto the graph. So that's 1, 1, and I'm going to put that here. Now with a normal enlargement, my construction lines would go from the centre enlargement through the shape and outwards in this direction. With a negative scale factor, they're going to go from the shape to the centre enlargement and outwards in this direction. That tells me that my finished picture is going to be here somewhere. I also know that because the scale factor has a 2 in it, all the lengths are going to double. Now I can start drawing my construction lines. So I'm going to draw a line from this corner through the centre enlargement, and I'm going to carry it on downwards. So now I want to focus on the distance from the centre of enlargement to the corner. I can see this is 1 square. So now I've got to go from the centre of enlargement to my new corner, double the amount. So that's going to be 2 squares. So this will be the new corner. I'm going to do the same process for this corner here. Now I'm focusing on the distance from the centre of enlargement to this corner here. I can see that's 1 diagonal over 1 square. Remember, I've got to double that, so that's going to be 2 diagonals, and that will be here. Now that I've got 2 corners, I can join them together. Now I want to repeat the guideline process for the final corner. Again, I want to find the distance from the centre of enlargement to the corner. I can see that's a diagonal over 3 squares, so I need to double that, and I get my new corner here. I can now join this to the other 2 corners. So this is my finished triangle. You can see that the lengths of all the sides have been doubled, and the effect of the negative scale factor is to make the triangle upside down in the image. Here's one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. Be very careful to join the points up as you go along on this one. Press pause and have a go. When you're ready, press play. Here's the answer. I'm being asked to enlarge this triangle here by scale factor -2 with centre of enlargement 1, 1. I'm going to show you a way of doing this using vectors which will work for every question. The most important thing is the centre enlargement. That's 1, 1, and I'm going to mark that very clearly on the diagram. Remember, this is the most important point now. Now what I need to do is choose a corner of my triangle. I'm going to pick this one here, and I need to write a column vector to get from the centre of enlargement to that corner. So I can see that I don't go across at all, I just go up 1. So the column vector is 0, 1. Remember, the top number means left and right, the bottom number means up and down. Now I want to multiply this by the scale factor, which is -2. So I've got -2 times this column vector. -2 times 0 is 0, and -2 times 1 is -2. So now I go back to the centre of enlargement and I use this vector. So it's 0, that means across none, and -2 means down 2. So I go down 2 and I put my new corner. So this is where this corner will be on the enlarged shape. Now I'm going to do the next corner, so I'm going to do this one here. Remember, back to the very important centre enlargement and write a column vector. So it's left 1, up 1. So the column vector is -1, 1. This is left 1, this is up 1. I've got to multiply that by the scale factor. So -2 times -1 is 2, and -2 times 1 is -2. Now back to the centre enlargement, and I use this column vector. So that's right 2, down 2. So right 2, down 2. Now that I've got two corners, I can join them together. And now I need to do the third corner, that's this one here. So again, I need to write a column vector to get to it from the centre enlargement. So it's left 1, up 3. So that's -1, 3. And I multiply this by the scale factor. So I've got -2 times -1, that's 2, and -2 times 3, that's -6. Back to the centre of enlargement and use this. So that's right 2, down 6. So right 2, down 6 is here. And this is my third corner. I can join it to the corner that I've just drawn, and join to the final corner to complete the triangle. This is my finished enlargement. Now the lovely thing about this kind of question is that there's a really nice way of checking your answer. If you join each corner on the small triangle to the corresponding corner on the large triangle, all the lines should cross through the centre of enlargement. It looks like this. And you can see that my green lines all cross through the centre of enlargement, so I can see that this is in the correct position. I also need to check the size of it. I'm enlarging by a scale factor of -2. The 2 part of this means that all the lengths will double. So if I look here, I've got a length of 1 square, and on my new shape, it's 2 squares, so that has doubled. Here I've got a length of 2 squares, and on my new shape, that's 4 squares, so that has doubled. The last side will automatically double if we get the other 2 correct. Notice the effect that the negative scale factor has. It means that the triangle is upside down in the enlarged image. Here's one for you to try now. You'll need to copy the triangle and the axes onto some squared paper. Press pause and have a go. When you're ready, press play. This is what your answer should look like. Here's another question for you to try. Again, you'll need to copy this onto some squared paper. Be really careful that you join the points up as you go along. Press pause and have a go. When you're ready, press play. This is what your answer should look like. Here's a really tricky looking question on transformations. I'm being told that triangle A is reflected in the x-axis to give triangle B. Then triangle B is reflected in the line x equals 1 to give triangle C. I want to describe fully a single transformation that maps A onto C. I'm going to do this line by line. So the first thing it says is triangle A is reflected in the x-axis to give B. So first of all, I'm going to actually do that reflection on here. So here's the x-axis, and I want to reflect A in it. The reflection looks like this, so this is triangle B. The next line tells me that triangle B is reflected in the line x equals 1 to give triangle C. Now the hard bit here is finding the line x equals 1. Remember, this is a vertical line that crosses the x-axis at the number 1. So it's going to be this line here. So I draw that line and then reflect triangle B in it to give this result. Now I've got to find a single transformation that maps A onto C. So I need to look at A and C. I can see that triangle A has gone upside down to make triangle C. So that means that this must be a rotation. Now this isn't enough. In the question it asks me to describe the transformation fully. That means I need to put in all the detail that I need to perform the rotation. So I need to know how far it's rotated. Because it has gone upside down, I know that's 180 degrees. Now I need one more thing, and that's the centre of rotation. By I, that's going to be a point that's midway between triangle C and triangle A. So I think it's this point here. I need to double check this though, and I'm going to use tracing paper to do that. So I trace shape A onto the tracing paper, and then I mark the point where I thought the centre was going to be, and I start rotating to see if the triangle ends up exactly on top of shape C. It does, so I know that this is the correct centre, and the coordinates are 1, 0, so I write that into my description. Out of interest, if this hadn't worked out, I would have just made another guess at where the centre is and tried again. Now I've got the type of transformation and all the information that I need to be able to perform it, so this is the finished answer. Here's one for you to try. You'll need to copy out the axes and the shape onto some squared paper. You can also use tracing paper to help you if you want to. Just one tip, the line y equals 0 is actually the x-axis. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. Again, you'll need to copy out the axes and the shape onto some squared paper. You can use tracing paper again. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. You'll see that you've got a grid here to help you, but you will need to be a bit creative to get the answer to this question. Press pause and have a go. When you're ready, press play. Here's the answer. To get this, I needed to invent my own shape and put it anywhere I wanted to on this grid. So I chose to use a small triangle and I put it here. I then rotated it 180 degrees about the origin and reflected in the x-axis. Then I looked to see how to get from this triangle to this triangle, and it was a reflection in the y-axis. Interestingly, it doesn't matter what shape you use or where you choose to start. It will always work out to be a reflection in the y-axis. There are 7 circle theorems that you need to know about. These are some of the most frequently occurring types of exam question. Pupils tend to find them really difficult, but that's often due to lack of practice. So in this clip, we're going to make sure we do them enough to be able to remember them. Let's look at this first one. When a radius meets a tangent, the angle that it makes will always be 90 degrees. Obviously, this works for diameters as well. Using this circle theorem, try to answer this question. Press pause and have a go. When you're ready, press play. Here's the answer. To get this, I spotted that there's a right angle here of 90 degrees, and then there's a triangle which must add up to 180 degrees. This second circle theorem is also fairly straightforward. From a point that's outside the circle, 2 tangents can be drawn. From the point to where they touch the circle, the tangents will be equal in length. Can you now use this fact to answer this question? Press pause and have a go. When you're ready, press play. Here's the answer. You should have spotted that because the tangents are equal in length, we have an isosceles triangle. So this angle here is 40. We then know that the angles in a triangle must add up to 180, and this gives us the 100 degrees. Now let's move on to the third circle theorem. The angle subtended at the centre of a circle is twice the angle at the circumference. Subtended just means made. So in other words, the angle here is double the angle here. Now when it looks like this, it's fairly easy to remember and easy to spot. But sometimes the questions might look a bit different. These three diagrams here all show the same situation as this, just in different ways. So here, this angle will be double this angle. If we move this point round the circle a bit, we get this picture. And this angle is still double this one. This one here is the hardest to spot. We've still got an angle at the centre here, and it's still going to be double the angle at the circumference. Now use this theorem to answer this question. Press pause and have a go. When you're ready, press play. Here's the answer. You should have spotted that this will be double this. Now we're ready for the fourth circle theorem. The angle in a semicircle is a right angle. This just means that if you put a diameter anywhere on the circle and make a triangle that touches the circumference, you'll always get a right angle. Now here's a question involving that circle theorem. Press pause and have a go. When you're ready, press play. Here's the answer. You should have used the circle theorem to realise that this is 90 degrees, and then we've got a triangle which must add up to 180. Now for the fifth one. Before we look at the circle theorem, I just want to quickly revise what segments are. If we draw any chord on the circle, we make two segments, one here and one here. What the circle theorem says is that angles in the same segment are equal. What this means is that if I draw my chord here, I've got two angles here that are in the same segment, and they will be the same as each other. Using the same diagram, we can turn it upside down and draw the chord here and get two different angles that are still the same as each other. Or you might even have a situation where you've got three angles coming off the same chord. They're still going to be the same as each other. Now try this question using that circle theorem. Press pause and have a go. When you're ready, press play. Here's the answer. You should have spotted that we can draw a chord here, so these two angles are in the same segment, making them the same as each other. Now for the sixth circle theorem, and this one's a tricky one. This one's called the alternate segment theorem, and just like the last one, it uses segments. If you draw a tangent to a circle, and then draw any chord that touches that tangent, you make an angle here. Now this angle is in this segment of the circle. The angle in the alternate segment, which is this one over here, will be equal. We can also look at this same diagram in a slightly different way. If we look at this chord with the tangent, we've got this angle here, which is in this segment. This angle is in the alternate segment, and it will be equal to this one. We still have a tangent and a chord, making an angle, and the angle in the alternate segment will be equal to it. Don't forget that the tangent doesn't have to be horizontal to make this work. Now try this question. Press pause and have a go. When you're ready, press play. Here's the answer. You simply need to spot that this is the angle in the alternate segment to this one. Finally, we're going to look at the last circle theorem. This one tells us that the opposite angles of a cyclic quadrilateral add up to 180 degrees. A cyclic quadrilateral is any four-sided shape drawn inside a circle where the corners all touch the circumference. Two angles opposite each other add up to 180, so we have one pair here and one pair here. Sometimes it's a bit harder to spot. This is still an example of a cyclic quadrilateral, so we'll have a pair here adding up to 180 and another pair here. Here's a question on that one for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. To get this one, you needed to take 78 away from 180, and to get this one, you needed to take 75 away from 180. Now we're going to look at lots of different exam-style questions on circle theorems. You need to spot which circle theorem it is and use this to answer the question. Sometimes you'll be asked to give a reason, in which case you can state the circle theorem. Sometimes you'll be asked to show your working. If this is the case, make sure you do it methodically. You might find it helpful to sketch the diagrams. When I go through the answers for these, I'll just be showing you one way, but there's often more than one method to get the right answer. Here's your first exam-style question then. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you. Press pause and have a go. When you're ready, press play. Here's the answer. For part A, you needed to realise that this angle here will be double this angle here, making it 140 degrees. For part B, you should have realised that because this is 140, this will be 220 because we've got 360 degrees here. You then know that the four angles inside a quadrilateral add up to 360, and you can use that to calculate the size of angle Y. Here's another one for you. Press pause and have a go. When you're ready, press play. Here's the answer. This one was a bit more tricky. You need to realise that these two lines are the same length because they're both a radius of the circle. That makes this an isosceles triangle, so this is 41 degrees to match this. You can then work out that this is 98 and use the fact that this is double this to work out the 49. Here's another one for you. Press pause and have a go. When you're ready, press play. Here's the answer. Drawing the chord here helps you realise that these are the angles in the same segment, so this is equal to this. Here's another one for you. Press pause and have a go. When you're ready, press play. You should have spotted the alternate segment theorem here. Here's an angle on a chord and tangent, so the angle in the alternate segment will be equal to it. That gives us an answer of 47 degrees. For the reason, you just need to write alternate segment theorem. Here's another one for you. Press pause and have a go. When you're ready, press play. For this one, quickly spot that you've got a right angle here, and then take away from 180 degrees to leave you the 28 degrees. Your reasons are that the angle in a semicircle is 90 for this part, and the angles in a triangle add up to 180, which is what helps you actually work out the 28 degrees. Here's another one for you. Press pause and have a go. When you're ready, press play. For this one, you needed to spot that the angle at the centre here will be double the angle x. That makes x 70 degrees. Your reason is what I just said. For part B, you should have spotted that x and y are two opposite angles of a cyclic quadrilateral, so you can take 70 away from 180 to leave you 110 degrees, which is y. Your reason is that the opposite angles of a cyclic quadrilateral add up to 180 degrees. Now here's a much more challenging question for you to try. Press pause and have a go. When you're ready, press play. To start this question, the first thing you need to spot is that we've got an alternate segment. We've got this angle here, 34, so this one here will also be 34 degrees. Now, where do we go next? Well, the thing is to spot these two little arrows here. They must be here for a reason, so we must have to use them. And we've got alternate angles. So if this one is 34, then this one is 34 as well. For our next move, we spot these little marks here. Again, they must be here for a reason. They're telling us that this is an isosceles triangle, so this is 34 degrees as well. Now, inside that isosceles triangle, we've got two angles of 34. 34 plus 34 makes 68 degrees. We can work out this angle here by taking the 68 degrees we've just worked out away from 180 degrees, and we get 112 degrees. Now we spot that we've got two opposite angles in a cyclic quadrilateral. These two must add up to 180. So 180 minus this 112 gives us 68 degrees, obviously because we've done it the other way round here. So the answer for x is 68 degrees. Here's another tricky looking one for you. Press pause and have a go. When you're ready, press play. Here are the answers for that one. Here's another one for you. Press pause and have a go. When you're ready, press play. For this one, we start with the alternate segment theorem here, so this is 75 degrees. Then we've got a straight line which makes 180, so we can work out this. We've then got a triangle, which is 180, so we can get this one. Again, there's another straight line here, that gives us the 50. To finish off, we've got the opposite angles in a cyclic quadrilateral, and that gives us the angle that we're looking for. Now here's the hardest type of circle theorem question that you might get. The trick for this one is to definitely do a little sketch of it yourself. Press pause and have a go. When you're ready, press play. Here's the answer. The key to this was to draw in this radius here, which forms a 90-degree angle with the tangent, and an isosceles triangle here. Here we have one of the circle theorems. The angle subtended at the centre of a circle, that's this angle here, is twice the angle at the circumference, that's this angle here. We want to prove it. Now when you do a proof, you need to do it very formally, but to be able to do that you have to understand how it works first. So I'm going to show you this informally to start with. To do this, I'm going to draw a line from C to O and carry it on down through the circle. Now, I have a radius of the circle here, and here, and here. Because these two lines are the same length, I know that AOC is an isosceles triangle. So this angle is the same as this angle, and I'm going to call those both x. Now this angle here must be 180 minus those two x's, because the angles in a triangle add up to 180. Then, on my straight line, we also have 180. So, this angle here must be 2x, because 180 minus 2x plus 2x gives me the 180. In the other triangle here, I've got two radii again, so this must be the same as this, and I'm going to call these y. In the same way as before, this angle here must be 180 minus 2y, and this angle here is 2y. Now we can see that the angle at the top here is x plus y, and the angle in the centre here is 2x plus 2y. So the angle in the centre is definitely double the angle at the top. I'm now going to show you how to write this in a formal way so that you would get full marks in the exam. So I start by writing that triangle AOC is an isosceles triangle, and that's because OC is equal to OA because they're both radii of the circle. So from this line, I know that angle OAC, that's this one here, is equal to angle OCA, that's this one here, because they're both base angles of that isosceles triangle. And I decided to call both of these angles x. So I'm going to write let angle OAC equal angle OCA equal x. Now I know that angle COA, that's this angle here, is equal to 180 minus 2x because the angles in a triangle add up to 180 degrees. Now I need to show how I got this 2x here. I need to be able to label this, so we've got AO, so I'm going to put a D here. So angle AOD is equal to 2x, and that's because the angles on the straight line here must add up to 180 degrees. I can now repeat this whole process for the other triangle, which I've done here. To finish, I need a concluding statement. So I write that angle AOB is equal to 2x plus 2y, and angle ACB is equal to x plus y. So angle AOB is 2 times angle ACB, and we now have our proof of the circle theorem. Now I want to prove this circle theorem, that the angles in the same segment are equal. What that means is that this angle here is equal to this one here. To do that, I first of all need the centre of the circle, and I'm going to draw a radius from O to A and one from O to C. Now, using the circle theorem that I proved a minute ago, I know that this angle here must be double this angle here. So if I call that x, this one is 2x. And, using the same circle theorem again, if this one's 2x, this one here must be half of it, which is x. And I can see that I've got the same angle in both places. I'm now going to write this in a more formal way. And the formal proof looks like this. We say let angle ABC equal x, that's this one here. We then know that angle AOC is 2x, that's this one here, and that's because the angle at the centre is twice the angle at the circumference. Then we know that angle ADC, this one here, must be x because it must be half of this one, and we write that the angle at the circumference is half the angle at the centre. So, angle ABC is equal to angle ADC because they're both equal to x. So we've proved that angles in the same segment are equal. I now want to prove that the opposite angles of a cyclic quadrilateral add up to 180 degrees. So to do this, I need the centre of the circle, and radius OD, and radius OB. I'm going to start this one by calling this angle here x. Then we know that this angle at the centre will be 2x. We also know that this angle here will be 360 minus 2x, and this angle at the circumference will be half of this one. Half of 360 is 180, and half of minus 2x is minus x. So I now have this angle and this angle opposite each other, and I can see that if I add them up, I'm going to get 180. Now I need to write this formally. So I start with let angle DCB, that's this one here, equal x. I then know that angle DOB, this one here, must be 2x because the angle at the centre is twice the angle at the circumference. Then the reflex angle here, that's reflex angle DOB, must be 360 minus 2x because the angles round a point equal 360 degrees. Then this angle here, that's angle DAB, must be 180 minus x because that's half of 360 minus 2x. The angle at the circumference is half the angle at the centre. Now angle DCB plus angle DAB is x plus 180 minus x, which is 180. So we've shown that opposite angles of a cyclic quadrilateral add up to 180 degrees. So in this clip, we've looked at 3 proofs of circle theorems. You may be asked to reproduce any one of these in the exam. If one shapes an enlargement of another, then they're said to be mathematically similar. For example, these 2 triangles here are similar. What that means is that this angle will be the same as this one, this angle here will be the same as this one, and this angle here will be the same as this one. This triangle is an enlargement of this one here. There's a formula for finding the scale factor of the enlargement, and it looks really complicated, but it's actually very straightforward to apply. To find the scale factor of enlargement of these two shapes here, I just need to find two corresponding sides with measurements on them. So I've got AC here and PR here, and they both have a measurement on them. To find the scale factor of the enlargement, I get this side here, and the length is 15, and I divide it by this side here, and the length here is 6. Now 15 divided by 6 is 2.5. So the scale factor of the enlargement is 2.5. That means if I want to go from the small shape to the big shape, I multiply by 2.5. And if I want to go from the big shape to the small shape, I divide by 2.5. Now that you have this to help you, you should be able to find the lengths of sides RQ and AB. Press pause and have a go. When you're ready, press play. So to find RQ, I can see that the corresponding side here is 10, so I multiply that by 2.5. 10 times 2.5 is 25, so the side RQ is 25 centimetres long. For AB, that's here, I can see the corresponding side is here, and that's 20. So I'm going to divide by 2.5. And 20 divided by 2.5 is 8. So AB is 8 centimetres long. Now I'm given two squares A and B. To start off with, I'm being asked to find the linear scale factor. Well, that's exactly what we've just done. We want to find the scale factor that links the sides or the lines. So we have this side here, that's 6, and we divide it by this side here, that's 2. And that tells us that the linear scale factor is 3. In the second part, I want to find the area scale factor. To do this, I need to find the area of square A. Now the area of square A will be 2 times 2, which is 4. And I need the area of square B. The area of square B will be 6 times 6, which is 36. So to find the area scale factor, I'm going to get this area here, 36, and divide it by this area here, 4. And I get that the area scale factor is 9. Here's a question for you to try. Press pause and have a go. When you're ready, press play. So for the linear scale factor, we have 12 divided by 3, which is 4. To find the height of triangle B, I'm going to use the height of triangle A and my linear scale factor. So we have 2 multiplied by 4, which is 8. So the height of triangle B is 8 centimetres. To find the area scale factor, I need the areas of both triangles. Remember, the area of a triangle is base times height divided by 2. So for A, I've got 3 times 2 divided by 2, which is 3. And for B, I've got 12 times 8 divided by 2, which is 48. So to find the area scale factor, I've got 48 divided by 3, which is 16. So in the questions that we've just done, when we had a linear scale factor of 3, the area scale factor was 9. And when we had a linear scale factor of 4, the area scale factor was 16. You've probably noticed that the area scale factor is always the square of the linear scale factor. You need to make sure that you know this fact for the questions that are coming up now. So I'm now going to use this fact to help me answer this question. I've got a small octopus transfer. It's got a height of 15 centimetres and a surface area of 250 centimetres squared. There's a mathematically similar large octopus transfer, and that's got a height of 75 centimetres. And I want to work out the area of the large transfer. So the height of the small one is 15, and the height of the large one is 75. So if I can find the link between these two numbers, I've got the linear scale factor. Now 75 divided by 15 is 5. So that's the linear scale factor. Now remember, I want to work out the area of the large transfer, so I'm going to need the area scale factor. And remember, the area scale factor is the linear scale factor squared. So that's going to be 5 squared, which is 25. So the area of the small octopus is 250, and to find the area of the large octopus, I'm going to multiply that by 25. And I get 6,250 centimetres squared. This is the area of the large transfer. Here's a question for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. Here's another question for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. I hope you realise that this time they were giving you the surface area of the larger pyramid. So you needed to divide by the area scale factor to get the answer. Now I have cubes A and B. I want to find the linear scale factor. We know that that's 6 divided by 2, and 6 divided by 2 is 3. I also want to find the volume scale factor, so for that I need the volume of both cubes. The volume of A is 2 times 2 times 2, which is 8. The volume of B is 6 times 6 times 6, which is 216. So to find the volume scale factor, I've got 216 divided by 8. And 216 divided by 8 is 27. So we've already seen that when the linear scale factor was 3, the area scale factor was 9. And we've just seen that the volume scale factor was 27. Now we know that this was this number squared. Is there a link between this number and this one here? Well, yes, you should be able to spot that this is 3 cubed. So the volume scale factor is the linear scale factor cubed. So here's an exam-style question. I'm going to use this fact to help me answer it. For this one, I would be allowed a calculator. I've got the heights of the two different size dinosaurs here, 10 and 12, so I can find the linear scale factor from 10 to 12. Now 12 divided by 10 is 1.2, so the linear scale factor is 1.2. I'm asked to find the volume of B, so I'm going to need the volume scale factor. So remember, the volume scale factor is the linear scale factor cubed. I would use a calculator to get this answer, and that's 1.728. So now to find the volume of B, I'm going to get the volume of A, that's 600, and multiply it by the volume scale factor, which is 1.728. Again, I would use a calculator for this, and I'd get 1036.8 centimetres cubed. This is the volume of this solid. Here's one for you to try now. Again, you can use a calculator to help you with this. Press pause and have a go. When you're ready, press play. Here's the answer. Here's another one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer. We know that if we see a right-angled triangle set up like this, we can use trigonometry to find a missing side or a missing angle. In this clip, we're going to be looking at using more advanced trigonometry to find missing sides and angles in non-right-angled triangles. In particular, in this clip, we're going to focus on using something called the sine rule. The first step in using the sine rule is recognising when you actually can use it. I've already said that you can use it in non-right angle triangles. The thing to remember about the sine rule is that it's all about opposites. So for example, if we look at this one, the side I'm looking for is opposite this angle here, which I'm given. And I'm given another opposite pair, this side and this angle. So I can use the sine rule here. Looking at this one, the angle I'm looking for is opposite this side, which I'm given, and I have another opposite pair, this angle and this side. So again, I can use the sine rule here. To be able to use the sine rule, we're going to need a formula. Let me show you how we get that formula. We start with any side divided by the sine of the opposite angle. And that will be equal to any other side divided by the sine of the opposite angle for that side. And that will also be equal to the third side divided by the sine of the opposite angle for that side. I told you this was all about opposites, didn't I? Now, if we label our triangle more formally, using lowercase letters for the sides and uppercase letters for the opposite angles, then we can create a formula. And we use this version of the formula to find any of the three sides. If you're actually looking for an angle rather than a side, then we simply flip the formula to get this. Now, a really important point about the sine rule is that when you're doing a question, you only ever need two of these three things. So, for example, you might be using the A's and the B's, but you won't use the C's. Or you might use the A's and the C's, but not the B's. The two that you use will depend on the question that you're given. I'm now going to take you through a typical question using this rule. I can see here that I've got an angle and an opposite side, and I've got an angle and I'm looking for the opposite side. Because it's all about opposites, I'm going to be using the sine rule. I'm looking for a side, so I'm going to be using this form of the sine rule. So the side I'm looking for is x. I start by writing that down. And that's going to be over the sine of the opposite angle, which is 28. Then that's going to be equal to the other side that I've got, which is 9, over the sine of the opposite angle, which is 76. To get the answer, I need to rearrange this to make x the subject. So what I'm going to do is multiply both sides by sine 28. So I get 9 times sine 28 over sine 76. It's now just a case of using my calculator correctly to get this answer. You'll notice that in this question, I'm not told how many decimal places or significant figures to round my answer to, so I'm just going to round it off to 3 significant figures. I get 4.35. Now what I've found is the length of a side, so the units for it must be centimetres. Here's one of those for you to try now. Press pause and have a go. When you're ready for the answer, press play. So you're looking for the side x, so start with that, and that will be over the sine of the opposite angle, which is 31. This is going to be equal to the other side, which is 19, over the sine of the opposite angle, which is 112. Rearranging to make x the subject gives us 19 sine 31 over sine 112. And typing this carefully into the calculator and rounding to 3 significant figures gives us an answer of 10.6. Because it was a side that I was looking for, the units are centimetres. Out of interest, if you followed this through exactly and still got the wrong answer, it might be that your calculator is in the wrong mode. You need to make sure that your calculator is set up in degree mode. Also, if your calculator opens a bracket after you've pressed the sin button, you've got to make sure that you close it again. That might happen here as well. Now in this question, I'm looking for an angle here. I could use this version of the sine rule, but it's actually a lot easier if I flip it like this before I start. Now the angle I'm looking for is y, so I start here with the sine of y. And this is going to be divided by the opposite side, so that's 14. That's going to be equal to the sine of the other angle that I've got, that's 83, divided by the opposite side, that's 17. Now I can rearrange this. So sine y will be equal to 14 sine 83 over 17. So y equals inverse sin of 14 sine 83 over 17. Typing this into the calculator carefully and rounding to 3 significant figures gives me 54.8. This time it's an angle, so the units must be degrees. Just in case you've forgotten how to do inverse sine in your calculator, remember for this part you need to press Shift and then the sin button. Here's one for you to try. Press pause and have a go. When you're ready, press play. Here's the answer, which I've rounded to 3 significant figures. We're now going to look at some exam-style questions. In the exam, you won't actually be given the formula. So here's your first real exam-style question. In this question, you're looking for the length of the side LM. One tip for you is to label the side LM with an X. Press pause and have a go. When you're ready, press play. Here's the answer. Now, the best way to get good at the sine rule is to practice, so here are 4 more questions for you. Press pause and have a go at them. When you're ready, press play. Here are the answers. Now here's a more difficult question for you to try. You need to use a bit of imagination on this one. You won't be able to get the angle you're looking for directly, but you will be able to find it if you remember that the 3 angles in a triangle always add up to 180 degrees. Press pause and have a go. When you're ready, press play. The first thing you should have noticed in this question is that you've got a pair of opposites here, so you know you're going to be using the sine rule. We're looking for the angle ACB, so I've labelled that as X. If I look at the diagram, I haven't got the side opposite that, but I have got this side, which is opposite this angle, which I've called Y. So I used the sine rule to find the angle Y first of all, and I got the answer 23.24 degrees. So I know that this angle here is 23.24 degrees. To find the angle I'm looking for, all I have to do is remember that there's 180 degrees in a triangle. So if I take this and this away from 180, I get the angle that I'm looking for. To 3 significant figures, the answer is 14.8 degrees. Now this is the hardest kind of question that you will see on the sine rule. I'm going to give you one clue, and that's that you're going to actually have to use the sine rule twice in this triangle. Press pause and have a go. When you think you've done it, press play. To start this question, I'm looking for the length of AC, so I'm going to label that X. Now this side is opposite this angle over here, so I'm going to label that Y. I've got one pair of opposites here, but for this side that I'm given, I don't know this angle. So my plan is this. I'm going to find this angle here first, then use this to find this angle, and then use this angle to find this side. So the first thing I want to do is calculate the size of angle Z, and I'm going to use the sine rule to do this. I get the answer 34.50 degrees. I've rounded this to 4 significant figures because I want my final answer to 3 figures. So I now know that angle Z is 34.50 degrees. The next thing I want to find is the size of angle Y, and I'm going to use the fact that the 3 angles in the triangle must add up to 180 degrees. So Y will be 180 minus 136 minus 34.50. I get the answer 9.50 degrees, so this is the size of angle Y. Now I want to use the sine rule again to find the size of angle X, which is opposite angle Y. I get the answer 3.73 rounded to 3 significant figures. This was the length of a side, so the units are centimetres. Notice that when I did this question, I used this pair because I had to, because I was looking for X. But for the other pair, I chose these two that were originally given to me in the question. I could have used this pair if I wanted to, but I decided to use these ones. When we're using advanced trigonometry in non-right-angle triangles, there are 2 techniques that you need to know: the sine rule and the cosine rule. It's really important to be able to tell when to use which one. The way to remember the sine rule is that it's all about the opposites. We use it when we have a side with an opposite angle and another side with an opposite angle. The way to remember when to use the cosine rule is that it's all about being included. We use this when we've got 2 sides and the angle in between them. We call this the included angle. In this clip, we're just going to focus on using the cosine rule. This is the formal formula for the cosine rule, which you will see in textbooks and on formula sheets, etc. It's important to realise that lowercase letters are sides and uppercase letters are angles. To be able to use this formula to find a side, you need the other 2 sides and the angle between them. Let me show you what I mean. If I want to find the length of this side here, I need to know the lengths of these 2 sides and the size of the included angle. If I wanted to find this side, then I'd need these 2 and this angle. And for this side, I'd need the other 2 sides and the included angle. Let me show you how this works in much more detail now by doing a real question. So in this question, I want to find the length of the side X. I can see that I've got the other 2 sides and the included angle, so I know that I can use the cosine rule. I'm going to use the formula here as a guide to setting up the question. So the side I'm looking for is X. That goes here, so that's X squared. This is equal to either of the other 2 sides. I can choose this one or this one. I'm going to pick this one. Plus the other of the other 2 sides, so that's this one now. And you'll notice they're both squared. Take away 2 times both of the sides, so that's 16 and 23, times by the cosine of the included angle, that's 112 degrees. I can now type this into my calculator and get that X squared equals 1060.710453. It's really important to keep this on your calculator screen at this stage because you'll notice that what we found is X squared and we actually only want X. So the final step is to square root it. So I now find the square root and round it to 3 significant figures and I get the answer 32.6. This was the length of the side X, so the units must be centimetres. It's always a good idea to check that your answer is reasonable because some people forget this last step. If you think that this 1060 is the length of this side, you might suddenly realise that it's a bit big and that you've forgotten to square root. Finally, if you type this into your calculator exactly like this and don't get this answer, then your calculator is probably in the wrong mode. You need to make sure that your calculator is set to degree mode. Here's one for you to try now. The first thing to do is notice that you're looking for the length of the side LM. That's this side here, so you'll want to label that X. Press pause and have a go. When you're ready, press play. I can see that in this question I'm looking for a side and I've got the other two sides and the included angle, so I know I can use the cosine rule. I'm going to use this to help me set it up. X goes here, so that's x squared. This is equal to the other two sides squared and added together, so that's 21 squared plus 14 squared. Minus 2 times the other two sides, so that's minus 2 times 21 times 14, times by the cosine of the included angle, which is 134. Typing this into my calculator gives me that x squared equals 1045.459122. To find x, I now need to square root this number. I round it to 3 significant figures and get 32.3. This is the length of x, so the units are centimetres. Now, in the exam, you won't actually be given the formula for the cosine rule, so you need to make sure that you've remembered it. I'd now like you to try this question. Press pause and have a go. When you're ready, press play. Here's the answer. We've now looked at how to find a side using the cosine rule, and it's reasonably straightforward as long as you memorise this formula. What we're going to look at now is finding the size of an angle using the cosine rule. This is a little bit more difficult. Before I take you through this question, we need to look at the formula that we would use for finding an angle using the cosine rule. Now you've got two choices. You can either memorise this formula, as well as memorising this one for a side, or you can learn to get this formula from the one that you've already memorised for finding a side. So this is the formula that we've already memorised for finding the length of a side. I need to rearrange this to make cos A the subject, because cos A is the part with the angle. So the first move is to take this to this side and this to this side. So I get 2bc cos A equals b squared plus c squared minus a squared. Now to make cos A the subject, I just need to divide by 2bc. So I've got b squared plus c squared minus a squared divided by 2bc. So remember, you definitely need to learn this formula. You can then either learn this one as well, or learn how to get it from the original formula. So going back to our question, we want to find the size of angle PQR. PQR is this angle here. I'm going to call that X. Now the two sides that make the included angle are this one and this one. That tells me that these two are B and C, and this one is A. I now substitute into the formula. So cos of the angle I'm looking for, which is X, is equal to b squared. I said that that was going to be that one, plus c squared, that's the other one that's attached to the included angle, minus a squared, that's the side opposite to the angle. This is divided by 2 times b, which is that number, times c, which is that number. When I type this into my calculator, I need to put brackets here and here, and here and here. Typing this in gives me that cos x is equal to 0.7307692308. It's really important to keep this on your calculator because we now need to find x. We find x by doing the inverse cos, so we press Shift cos for this answer. We get 43.0, which I've rounded to 3 significant figures. Because this is the size of an angle, the units must be degrees. The important thing to remember for this is that the angle tells you which are the two sides B and C, because it must be included. Some people like to label, so this would be B, this is C, and of course that makes this one A. Once you've got this, you just need to substitute the values into your memorized formula. Here's one for you to try. I've put the formula for you to use up here. Press pause and have a go. When you're ready, press play. Here's the answer. Here are 2 questions for you to try now. Remember, on the real exam, you won't be given the formula, so you need to memorize this. Now try the 2 questions. Press pause and have a go. When you're ready, press play. Here are the answers. Now, the best way to get good at the cosine rule is to practice, so here are 4 more questions for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Here's a very challenging question for you to try now. The only clue I'm going to give you is that you're going to have to use Pythagoras as well as the cosine rule. Press pause and have a go. When you're ready, press play. Here's the answer rounded to 3 significant figures. The first stage was to find the length of side x using the cosine rule. I get this, and I've left it like this because it's not the final answer yet. Then I use Pythagoras in this triangle to work out the size of y. I get this, and again, I've left it like this because it's not the final answer. Finally, to calculate the perimeter, I add the 4 sides of the shape together. At this point, I can round my answer off. We already know how to find the area of a triangle using half the base times the height. But what if we don't know the height of a triangle? There is actually another formula for finding the area. This involves using any 2 sides and the angle between them. These would be the 2 sides A and B, and this would be the angle between them, so that's C. Let me show you how it works. So here we have a triangle, we've got 2 sides, and we've got the included angle, so we can use this to find the area. So the area is half times one of the sides times the other side times the sine of the included angle. All we need to do now is type this into our calculator. Rounded to 3 significant figures, the answer I get is 64.2. This is the area of the triangle, so the units are centimetres squared. If you try doing this and type it in exactly like this, but don't get this answer, then your calculator might be in the wrong mode. You need to make sure that your calculator is set to degrees mode. Now, the only really difficulty is that you're not given this formula on the exam, so you need to make sure you memorize it. Here are 2 questions for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. I'm being asked to find the length of BH in this cuboid. So in order to find this, I need to use this right-angled triangle here. Because this is a right-angled triangle, I'll be able to use Pythagoras to find this length here. I'm going to convert my 3D diagram into a 2D diagram. So this is the right-angled triangle. I've got B here, D here, and H here. And I'm looking for BH, which is this. To use Pythagoras, I need to know the lengths of the other two sides. DH is 4 centimetres, so I know that one. If I knew this one, I'd be able to do it, but at the moment I don't know the length of BD. So I need to go back to my 3D diagram and see if I can work out this length here. I can see that this length BD is the hypotenuse of this right-angled triangle here. So again, I should be able to use Pythagoras to find this length. I'm going to convert my 3D diagram into a 2D diagram again. So I've got BC, and I've got D here, and this is the right angle. The one I'm looking for is BD. Now BC is 12, and DC will be 3. I can now use Pythagoras to find this length. So I have y squared equals 12 squared plus 3 squared. So I get 144 plus 9, which is 153. Now y will be the square root of 153, and I'm going to leave that like this. Now remember, y is actually BD, so I can put that on here. I know that it's root 153. Now I can use Pythagoras on this triangle to find the length that I was looking for. So using Pythagoras, I have x squared equals this squared, and now you can see why I've left it as root 153, because I've got root 153 squared, and we know that the answer to that is going to be 153 plus 4 squared. So this is 153, and this is 16. Adding them together gives me 169. I can now square root this to find x, and that's 13. So the length BH that I was looking for is 13 centimetres. Just out of interest, when your 3 lengths, length, width, and height, are all at right angles to each other, then you can use one step to get the answer. You can say that x squared is a squared plus b squared plus c squared. So this gives me 12 squared plus 3 squared plus 4 squared. If I work this out, I get 169, and then I can find x by square rooting, and I get 13. So notice how using this method, I get the same answer, but using just one step. Remember, this works when your length, width, and height are at right angles to each other. Here's a question for you to try now. This question could be on the calculator paper or the non-calculator paper. Try it without a calculator, and if you get stuck, you can use one to help you. Press pause and have a go. When you're ready, press play. Here's the answer. I've shown you the working out using both methods. Here's another type of question for you. This time, you're looking for the height MT, which is this here. You're told that the sides of the base are 10 centimetres long, so this is 10 centimetres, and this is 10 centimetres. And you're told that AT, BT, CT, and DT are all 13 centimetres, so this here is 13 centimetres. Now you need to use Pythagoras to find this height. You can use a calculator for this one, but I'm afraid you do need to do it the long way because the length, width, and height aren't all at right angles to one another. This angle here is not 90 degrees. Press pause and have a go. When you're ready, press play. So I'm hoping that you used this right-angled triangle here. And you should have drawn it in 2D. Like this. You should have then noticed that you don't know the length of AM, so you need to look for that on the 3D picture. That's this length here. Now the best way to find this is to actually find AC and then halve it to give AM. AC is the hypotenuse of this right-angled triangle. Again, you should have drawn this in 2D. Now we work out y using Pythagoras. Now because this is a calculator question, we can actually find the square root of 200. Notice that the question wants the final answer to 1 decimal place. So for this working out stage, I'm going to have 2 decimal places, and that's 14.14. Now remember, the length we're looking for is AM, and AM is exactly half of y. So we can now halve this to give us 7.07. I can go back to my original 2D diagram and put this on here. Now I can use Pythagoras to find x, which is the height of MT that I'm looking for. Pythagoras gives me this, which I can now solve to find x. I get this, so the final answer to the question is that the height is 10.9 centimetres. Here's another one for you to try without any help at all this time. Remember, you can use a calculator for this. Press pause and have a go. When you're ready for the answer, press play. Here's the answer. In this question, I'm given a cuboid and I'm asked to calculate the size of angle DFH. The first thing I need to do is actually identify this angle. So if I draw a line from D to F and then another line from F to H, I can see that the angle that I'm looking for is this one here. I'm going to draw this part of the 3D diagram in 2D to make it easier to see. So I have DH, HF is actually at a right angle to DH, and then I've got DF. Now remember, it was a right angled triangle, and I'm looking for this angle here. I've got H, F, and D. Because I'm looking for an angle in a right-angled triangle, I know that I'm going to be using trigonometry. I know the size of DH, that must be the same as BF, so it's 5 centimetres. If I know the size of either HF or DF, I can then use trigonometry to find x. Looking back at the 3D diagram, I can see that the easiest one of those two to find is going to be HF. HF is the hypotenuse of this right-angled triangle here. So again, I'm going to draw this in 2D. So it's a right-angled triangle, GHF, and I'm looking for HF. I know that HG is 5, and I know that GF is 12. Looking at this, I can find the side that I need by using Pythagoras. So I get that y equals 13. Remember, y is actually HF. That's this here on this diagram, so I can put the 13 here. Now that I've got the two sides, I can use trigonometry to find the angle that I'm looking for. I start by labelling my sides. This is H, this is O, this is A. I'm going to cross out H, I've got O and A, so that tells me I'm going to use my tan formula triangle. Now that I've got to this stage, I need to find out what x is. I do this by doing inverse tan. So I press Shift tan in my calculator and I get the answer 21.0 degrees. You'll notice that in the question, it didn't tell you how many decimal places or significant figures to give your answer to. If this is the case, just give 1 decimal place. Here's one for you to try. Press pause and have a go. When you're ready for the answer, press play. For this one, you should have an answer of 25.2 degrees. Now, this is a very challenging question for you to try. You're being asked to find the angle that the line DE makes with DB. So that's this angle here. To find it, you need this side and this side. To find this length here, you'll need to draw a 2D version of this right-angled triangle. You can find the missing side by using Pythagoras. To find this length here, you'll need a 2D version of this right-angled triangle. You can use trigonometry to find the missing side. Once you've done that, you can then use trigonometry to find the angle that you're looking for. Press pause and have a go. When you're ready, press play. Your final answer should be 22.2 degrees. In this clip, we're going to be looking at vectors. Now, this is a high-scoring topic on the exam, which pupils seem to do really badly on. So, this is the plan. We're going to start by getting a feel for vectors and understanding what they are. Then there will be a few relatively simple questions to help you understand them. And then finally, you'll learn that there's only really 3 things you need to know. This, and this. So no matter how difficult looking the question is, you need to remember that it always comes back to one of these 3 skills, and in this clip I'm going to show you how to do all of them. Here we have a list of scalar quantities and a list of vector quantities. Now you might not have seen either of these 2 words before, but can you see the difference between this group here and this group here? This first group of what we call scalar quantities just have magnitude. That means that they have a size. So length has a size, area has a size, and so on. This second group of what we call vector quantities are different because they have a magnitude and a direction. Remember, magnitude is size. So these quantities here have size and direction. If we look at 2 just to compare, let's say speed and velocity, because you might have come across these in physics, you'll see that the speed of a car just tells you how fast it's travelling. But the velocity of a car tells you how fast it's travelling and in which direction. In GCSE Maths, we're only going to be looking at the vector quantity of displacement. I'm going to explain what that is now. So this is a displacement vector. It shows the shortest distance from A to B. The length of the line is the magnitude of the vector. The arrow on the line gives you the direction of the vector. There are 3 ways that we can write the vector. With a letter A, like this. However, because this is a vector, we have to show that it's a vector and not just any old letter A. In print, such as in a book, it will be written in bold. When you're handwriting it, to show that it's a vector, you can write the A and then underline it. You can also write it like this. You can see we've got A and B, and the arrow on the top gives you the direction from A to B. The third way of writing them is like this, as a column vector. We've seen these before when doing translations and when doing transformations of graphs. This tells us to go 1 to the right and then up 3. And if we look at the diagram, to get from A to B, we go 1 to the right and then up 3. So on our diagram here, we know that vector AB can be written as A. What do you think vector BA can be written as? Because BA is going in the opposite direction to AB, but has the same magnitude, we can write it as minus vector A. This is one of the crucial points about vectors. The direction matters, and if you change the direction of a vector, then you change its sign. Just out of interest, if I wanted a numerical quantity for the magnitude of this vector, then I just need to work out the length of the line, and I can do that using Pythagoras' theorem. So the magnitude of this particular vector is root 10. Here are some questions for you to try now. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Just out of interest, if I wanted to write vector DC in terms of B, then I would write it as minus vector B. And that's because I'm reversing the direction of the vector and going in the opposite direction to the arrow. We're now going to look at adding vectors. Here we have two column vectors, vector A and vector B. If I want to draw vector A on this squared paper, I can put it absolutely anywhere I want to, as long as I go 2 to the right and then up 3. So I'm going to choose to put it here. In the same way, if I want to draw vector B onto the squared paper, I can put it absolutely anywhere as long as I go 1 to the right and down 2. I'm going to choose to put it starting from the same point as vector A. So that's here. Now if I want to add the column vectors A and B, I set it up like this. And of course, 2 plus 1 is 3, and 3 plus minus 2 is 1. So vector A plus B is this column vector, and I can draw this on the squared paper as well. Again, I'm going to draw it starting from the same point. So I get this. Now when you look at the diagram, it doesn't seem to make much sense. How can vector A plus vector B possibly add up to give us this? Well, the answer is, of course, that vector B can be anywhere that it needs to be. So I can move it into position at the end of vector A. You'll notice that vector A and B are now nose to tail. And now you can see that this is what you get if you add these two vectors together. We call this the resultant vector. So remember, when you're adding two vectors, to make it make sense, you need to put them nose to tail, and then you get the resultant vector. Here are some questions for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. Now let's look at multiplying a vector by a scalar. This is my column vector, and I want to multiply it by 2. So I would set it up like this. I'm going to multiply vector A by 2 to get 2 vector A. So I have 2 multiplied by the column vector. And we can see that 2 times 2 is 4, and 2 times 3 is 6. So the resultant column vector is 4, 6. So when I draw it on the diagram, I can start anywhere I want and go 4 to the right and 6 up. You'll see it's in exactly the same direction as vector A, it's parallel to it, but it's exactly twice as long. Just out of interest, this particular type of situation will become very important later on. If one vector is a multiple of another one, then those two vectors are parallel. Here are some questions for you. Press pause and have a go. When you're ready, press play. Here are the answers. Again, notice that my two vectors are parallel, and this is because minus A is a multiple of A. So by now, you should have a feel for vectors and understand what they are. and you've done a few relatively simple vector questions to help you understand them. So now we're ready to move on to typical exam questions, which will use these three skills. We're going to focus on writing vector expressions first of all. So in this exam style question, the first thing I want to do is express vector OB in terms of vector A and vector B. First of all, I'm going to draw vector OB onto my diagram. So that's here, and the direction is from O to B. Now I've got to find this vector in terms of vector A and vector B. So that tells me that I've absolutely got to use this vector and this vector to make the resultant vector here. So I can see that to get from O to B, I can go from O to A, and then from A to B. Notice that the letter at the start is the O, and the letter at the end is the B, and the letters in the middle match. So for vector OA, you can see that I'm going from O to A with the direction of the arrow. So that's just vector A. And for vector AB, I'm going along AB with the direction of the arrow again. So that's vector B. So vector OB in terms of vectors A and B is actually vector A plus vector B. Now for vector BO, I need to go from B to A, and then I need to go from A to O. Notice again that the first letter is this one, and the last letter is this one, and the letters in the middle match. Now for vector BA, I'm going against the arrow of vector B, so I must have minus vector B. And for vector AO, I'm going against the arrow of vector A, so I must have minus vector A. Now I can simplify this a little bit and write it as minus vector B minus vector A, because a plus and a minus together give me a minus. Just out of interest, I could have got this vector from the answer to this part here, because the vector BO is the reverse of the vector OB, so I want to reverse the direction of this. I do this by changing the signs, so I would have minus A and minus B. You'll notice that these two are equivalent. Here are some questions for you to try. Press pause and have a go. When you're ready, press play. Here are the answers. In this slightly harder question, I'm told that P is the point on AB such that AP to PB is in the ratio 3:1. So the first thing I'm going to do is just draw this onto my diagram. So I know that AP must be 3 times longer than PB. So I can draw this into 3 little sections like this, and then I know that that is the equivalent to 1 little section. Now the first thing I'm asked is to find the vector AB in terms of A and B. So to go from A to B, I've got to go from A to O, and then from O to B. Now A to O is here, but it's against the arrow, so it must be minus vector A. And O to B is here in the right direction of the arrow, so that's just B. So this is the vector AB in terms of vectors A and B. Now I want to find the vector OP. So the first thing I'm going to do is draw this onto the diagram. Now I can see that there are 2 routes that I could take to get from O to P. So I could go this way, from O to B, and then from B to P. Or I could go this way, from O to A, and then from A to P. Now if I take this route, I'm going to have to use part of BA. If I take this route, I'm going to have to use part of AB. Because I've already worked out AB, I'm going to opt for the second route. So now I want to start writing these in terms of A and B. Now I can't do this immediately because at the moment I don't know what vector AP is. But I do know that vector AP is 3/4 of AB. And I know that because I split this into 4 equal pieces and I want to go a distance of 3 of those pieces along it. So it's going to be 3/4 of the vector AB. Now vector OA is in this direction, so that's just vector A. And I've got 3/4 of the vector AB, which I worked out in the first part here. So that's minus A plus B. I'm almost there now, but I need to write my answer in its simplest form, so I need to do a little bit more work. So I've got vector A, and then I want to multiply this bracket out by 3/4. So I've got plus 3/4 times minus vector A, so that's minus 3/4 of vector A, and I've got plus 3/4 times plus vector B, so that's plus 3/4 of vector B. Now I can simplify a little bit more. I've got one vector A here minus 3/4 of vector A, so that leaves me with 1/4 of vector A, and I've got 3/4 of vector B as well. So this is my final answer. Just out of interest, one of the parts of this question that students find the most difficult is simplifying this here, 1 vector A minus 3/4 of vector A. Because I'm dealing with quarters, it might help you to think of 1 vector A as 4/4. Then you can do 4 take away 3 to get your 1. Another really important thing to note about vector questions is that when you come upon them in the exam, you will almost always be using results from part A to help you with results from part B and maybe even part C as well. Here's an exam style question for you to try now. In this question, you need to notice that you're told that PQRS is a parallelogram. This tells you that PS and QR are parallel and that QR is the same length as PS. The same applies for PQ and SR. Press pause and have a go. When you're ready, press play. Here are the answers. You'll notice that on part A, there are 2 different ways you can write your answer. Either of these is correct. On part B, there's lots of different ways you can write your answer. Here's another question for you to try. Part A is relatively straightforward. For part B, you're asked to prove something. To do this, you need to find the vector OX and the vector OY. And once you've got these 2 vectors, you should be able to make your proof. Press pause and have a go. When you're ready, press play. Here's the answer for part A. For part B, I've started by calculating OX and calculating OY. I now need to prove that the vector OX is 2/5 of the vector OY. So, I'm going to work out 2/5 of the vector OY. So that's 2/5 times this. Now 2/5 times 5A is 2A, and 2/5 times 5B is 2B. And you'll see that this is the vector OX. So I've now proved that 2/5 of vector OY is equal to vector OX, which is what I was asked to prove in the question. So if we go back to our plan now, we can now write vector expressions. And what we're going to do now is look at these 2 skills. Now these are so similar that we're actually going to be looking at them together. So in this question, I'm told that A, B, C, D and E are 5 points, and I'm given some vectors. I've got to write down a fact about the lines AB and DC. So if I look at vector AB, I can see that that's 2A minus B. And if I look at vector DC, I can see that that's 6A minus 3B. Now, looking carefully at these two, I can see that this is 3 times this. So DC is 3 lots of AB. Because 3 times 2A is 6A, and 3 times minus B is minus 3B. So DC is a multiple of AB, and that tells me that these two lines are parallel. Out of interest, you could have written that AB is a third of DC. But this still tells you that one is a multiple of the other, and so the lines are parallel. Now in part B, I'm being asked to write down a fact about the points A, B and E. In part A, I was being asked to write about lines, but here I'm being asked for points. However, I've got vectors up here, so I'm still going to use these, and I'm going to try to link these vectors to the 3 points that I want. So if I look carefully, I want points A and B, and I've got vector AB, so I'm going to write that down first of all. I also want point E, and if I look at the vectors I'm given, I've got this one with an E in it, and it's also got a B, which is another of the points I'm concerned with, so I'm going to write this vector down as well. Looking at these now, I can see that vector BE is 4 times vector AB. Because BE is a multiple of AB, I know that lines AB and BE are parallel. Now I've written down a fact here about the lines AB and BE, but the question didn't ask me about lines, it asked me about the 3 separate points A, B and E. So that means I need to dig a little deeper into what this means here. To help me, I'm going to draw a sketch. So let's say this is the line A, B. Now the line BE is parallel to it, so it must have the same gradient. However, they share a common point. They both have the point B, here and here. So as they both share point B, that tells me that BE must start where AB ends. In other words, the 3 points all lie on one single straight line. And this is the fact that I can write down about the points A, B and E. So using this, I was able to extend the line that I already had to say that the lines have point B in common, and so therefore the points A, B and E lie on a straight line. So to summarise, if one vector is a multiple of another vector, then they are parallel. Looking at this example here, I can see that AB is exactly 4 times CD, so these two vectors here are parallel. In an exam situation, I would write this as a concluding statement. Line AB is parallel to line CD because vector AB is equal to 4 times vector CD. To prove that 3 points lie on a straight line, you make 2 vectors out of them and show that these are parallel. You also need to state that they share a common point. So in this example here, I can see that the vector BC is exactly 3 times the vector AB. So that tells me that the 2 vectors are parallel. I also have points A, B, B and C. So I can see that they share a common point of B. This tells me that the 3 points A, B and C must lie on a straight line. In an exam situation, my concluding statement would say that A, B and C lie on a straight line because the vector BC is equal to 3 times the vector AB and they share point B. So we're now able to do these two things. For this one, remember you have to show that one vector is a multiple of the other. And for this one, show that the vectors are multiples of one another and that they share a common point. We're now ready to look at some really difficult exam-style questions. Here's a question for you to try now. Press pause and have a go at it. When you're ready for the answers, press play. Here are the answers. In part A, I wanted to find ON. I got it in terms of OA and AN, and then realised that to find AN, I would need AB. So AB is over here, and I realised that AN was 2/3 of AB. Once I'd done this, I could get my final vector. For part B, I'm being asked to use the letters O, N and D and prove that they're on a straight line. Now, I've already got the vector ON, that's up here, it's the thing I worked out in part A, so I've got it written in red here. I'm going to work out vector OD as well, and I've done that here by going from O to A to C, and then C to D, and I get this vector. Now I can see that OD, this vector here, is 3 times ON, this vector here. So I know that ON and OD are parallel, and they also have a common point, O, so OND is a straight line. Here's another question for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers. Here's another question for you to try. Press pause and have a go. When you're ready for the answers, press play. Here are the answers.